so that we can say, okay, this is the best, this company has in having the best profit, maximum profit, so it is doing performing very well. But service sectors, for example, several government organizations, healthcare sectors, we can say, and education sector, they are non-profitable. So how to assess the profit in that field? We are using the data envelopment analysis basically. So nowadays, what is the hot topic of the days? That what is the ranking? Okay, so if you are just going to the hotel, even we are saying that for a small students or small kids, if we are talking about, so the parents are very worried that in which school we are sending our kids, that which will give them a better education, which is the what is our priority. Based on that, they are selecting this school, and that is for the first second is we are saying for class first second class students also. Similarly, if you are going some trip, so you are just ranking so many hotels, and accordingly you are selecting based on your priority. If you are just going for your healthcare, you are just selecting the hospital for your visiting for your health, so that okay, which hospital is good, and according to your priority you are selecting that one. So this is the hot topic of the moment, basically how to rank the non-profitable, basically non-profitable institutes or non-profitable organizations to the so that everyone can just find out, okay, in our according to our priority, this is the best and we can go for that. For example, if we are talking about NRF ranking in the academic institutes, India Today, QS World ranking, so they are collecting the data, and based on the data they are just doing mathematics, and they are just apply some formulations, and based on that they are just giving the ranking for each institutes, academic institutes basically. So it is just a game of the data, that okay, we are providing the data to them and they are formulating it, and then they are just saying, okay, this is the NIRF ranking 1000, this is the NIRF ranking 100, and so on. Someone is going up, someone is going down, and yeah, every year they are doing it. So that is our aim basically here, how to be rank the this non-profitable organizations basically. Second is, as I already defined here, top hospitals in India. So there are some ranking agencies which are just collecting the data, and accordingly they will just rank the institutes or organization according to their priority. Because if you are just seeing the first second students and you are going for giving the admission for that students, so you are not saying, okay, what is the placement? You're saying how is the teachers, how are the infrastructure of it, they are providing which type of facilities, sports facilities or not having or not, like this one. So at a time the priorities are different. But if you are going for the college, so at a time you are just checking for the placement also, that okay, how is the teachers, what is the quality of teachers, and how is the, you can say, what is the placement basically, what type of degree they are giving to us, so that we can place in a or in a market specifically, so that we can just explore the market, and we can having some situation in our market that okay, we are placed here. Similarly, if you are going for the top hospitals, so at a time you are not going for the hospitals specifically by the name only, you are just seeking the doctors also, okay, they are providing a good facilities or not, they are hygienic or not. So accordingly they are just identify the data, and accordingly they rank them. Similarly for the hotels, you are just searching for the hotels, so many agencies nowadays, trip advisors, we can say, so many agencies are there. According to the data, they are just providing you a list of hotels, and in that one, according to your priority, you are selecting the hotel. So this is a nowadays it is a problem of, or you can say this is a use of an every person. So here we are using the mathematics, that's why mathematics for everyone here. And here we are just according to priority, we set, okay, which we can select the this school for our kids, this hospital for health, this hotel to visit, and so on. So why ranking is important, why they are doing that, I already discussed here. Because there's a very competitive market, so many hospitals you can find out, so many good reputed doctors you can find out, so many hotels you can find out, even in metro cities you can find out so many schools for the same level, and you are very much confused that in which we have to go, in which we have to visit. So that's why the ranking is very important, because we are just in living in a very competitive scenario, and we have to improve this initiatives. For improvement we have to take, so that we can just survive in a competitive market. So, and other things also we can say, because if you're just going for the hotels, so hotels also having some award system. If you're going for the academic institutes, though they have the award system, so you are also saying, okay, we received this award, our institute received this award, our school is received this award. So accordingly they have to improve, and they have to just take the initiatives, they assess the performance. So these are the specific, we can say, the some possible reasons that ranking is important for every person in every field specifically. So to survive in such a competitive environment, so regular assessment of our organization, of our individual person is very important, and then we can just go into the competitive market specifically. And how we can just rank? Now the thing is coming. So first is perception based. Perception based is that what is your priority according to that, it is settled in your mind, and you are just saying, okay, this is my perception, like, okay, this school is very good. You are not searching the data, and your perception is, okay, my elder son was in that one and it was very good, so that's why you are just giving to other person. That is known as a mouth publicity also, that okay, that school was very good, that institute college is very good, and you can go for that, that hospital is very good. So that is completely perception based, there is no data required for that. But if you are using the mathematics based on the data, if you are trying to find out, so at that time you have to find out the efficiency score for each organization, and based on that efficiency score you have to rank them specifically. So there are several methods basically to assess the efficiency score. So first is perception means nothing is required, only you have to set your mind according to your perceptions, your priorities, and you are going for that. But if you are just taking according to the data, so you have to use the mathematics. So that is for everyone specifically. So first method which we can say ratio analysis, second is least square method, and third is parametric analysis, and the fourth one which we discuss here, that is the data envelopment analysis. So ratio analysis is also very easy method. For example, if you are seeing the mileage, if you are just going for the car, so you are checking for the mileage. Mileage is what? That what is the fuel consumption per kilometer? That is the our mileage, that okay, this is giving this mileage, and this mileage is very good, so that car is also good. So that is the ratio analysis, that that is simple two-dimensional measure. You are just taking, okay, how many fuel they are using to just in 1 kilometer, or this 1 liter they are use the this number of kilometers. So that is the, we can say, the ratio analysis. So if you're just purchasing a car, a very simple, again a very simple example I am saying, so many cars are in market, you are purchasing a one car, so you are just seeing the so many priorities. The car should be, what is the interior, what is the mileage, how is the look for that, okay, 5-seater, 7-seater, 3-seater, like that. So at a time ratio analysis if we are doing, so we are just doing only for two dimensional, that okay, mileage is this, look is this, only this. So many criteria are coming, and we can't overall access, or we can't give the overall ranking for particular car specifically if we are doing the ratio analysis. So it can't capture the complete effect of the all factors basically. Next is the least square method. It will just give the identify the central tendency of that. If you're having the 5-6 cars and you're saying, okay, this is the mileage is this and other things are this. So they're just giving, okay, they are making a fitting a line, fitting a curve. You know very well in the mathematics that least square curve we are making. And based on that least square, they are giving the central tendency. What is the mean of it? What is the mode of this? Median is this, and accordingly you can choose, okay, how far our value, our priorities from that linear curve. So that is also fail to identify the efficient organizers, how to rank them specifically. Third is parametric analysis that we are doing in the economics basically, because in the economics we are using this ranking method since a long time. So at a time they are just making a parametric way, but in that one that there is a function required, which is the relationship between, which showing the relationship between the dependent variable and independent variable, that y is equal to fx. And what is that f basically? So if you are going in a complex situations, for example our academic institutes, for example our healthcare sectors, for example our bank services, so at the time it is very difficult, the output can be described by any function of the inputs. Definitely a relationship exists, but what function we have, we don't know. A linear or non-linear, non-linear of what type, parabolic or quadratic, or what type of function, we are not able to identify. So that is the very big problem with the parametric analysis. Second is which parameter we are taking, we have to identify the distribution of that. That is also very difficult task in the parametric analysis. So we are coming to the data envelopment analysis. It is a non-parametric method and it is completely based on linear programming problem. And first problem which we discussed in the ratio analysis, it is only two-dimensional. So data envelopment analysis can handle multiple inputs and multiple outputs. Several inputs and several outputs you can take, and accordingly you can rank the that organization specifically. It doesn't require any assumptions of the functional form of relating inputs and outputs, just like in a parametric form. Inputs and outputs can have different measurement units. For example, if we are talking about the academic institutes, I will also give you the example in the applications. So of the institute, in that one, number of teachers is different. Research grant that is coming in a rupees, that is different. So both are the different measurement unit. And in mathematics, everyone knows that units having a very important role. So in data envelopment analysis, basically we can use different measurement units, and that will not affect so much because it is a ratio analysis, the extension of the ratio analysis. Next is the it just give us single efficiency score of each organizations, and these organizations are considered as a decision making units. So in a short form we are saying DMUs. So here what we are trying to find out, the data by the data envelopment analysis, we rank the decision making units. For example, if you are just using the academic institutes, for example, if you are taking the NIRF ranking, so there are so many institutes, universities, and they are taking the decision because vice chancellor of each university should be there, director of each institute should be there. So they are taking the decision to take the initiative of the improvement. So that's why we are just saying, okay, this is the decision making unit, and we can just say, okay, there is a scope of improvement also in that one, and they can take the initiative for that. So that is a merit of the data envelopment analysis, that they can just characterize the single efficiency score for each DMU, and then they will also tell you what is the scope of improvement. If they are not efficient, so what is the pair for that, what is the benchmark for that, how they have to behave, or how to they work in which scenario, and you can find out that this is the benchmark for that particular organization, so that they can improve very well and they can become efficient. So that is also one benefit of the data envelopment analysis. So actually it is the data envelopment analysis, it is started in 1957, and they are just using the frontier analysis. Frontier analysis basically they are just collecting the data and make the frontier. And frontier is what? That is the making a surface basically on the data like this one, or they cover the complete data, and based on that surface they just analyze the data for each organization and then find out that okay, what is the ranking for that. So they are making a frontier surface and how far that particular DMU from that surface. If it is very far, so it is very inefficient. If it is very close to that frontier, so that's we can say okay, it is very close to the efficient one. So that concept is given by 1957 by the Farrell. But at the time it is a graphical notation only. We are saying we are just having the complete data set and we are just taking the surface on which. But it is not so much mathematical. So in 1978, Chance, Cooper and Rhodes gave the mathematical framework of this frontier analysis, and that is known as the data envelopment analysis. So that is the same thing actually. What is the meaning of data envelopment analysis? As I told you, by the frontier only. We are making the frontier, we envelop the complete data, and then we do the analysis. So that's why the meaning is data envelopment analysis. So we make the envelope over the complete data, and then when do I the analysis mathematically that okay, this particular DMU is very close to this envelope, so this is more efficient, and it is very far from that our frontier, so it is inefficient basically. And here we are using the linear programming problem. So I believe the 10+2 there, just nowadays in the NCERT book, linear programming problem is there in the syllabus. So when we are going to college specifically, so we can use this mathematics here. So it is not a very big rocket science of this type of definitions and rockets are very complex type of a mathematics, simple linear programming problem. So a 10+2 student can understand and they can do it is there. After that, because every model which we are giving based on the real life, because this is a completely application based model. So Chance, Cooper, Rhodes gave the concept of the constant returns to scale. That's I will discuss later on. So that is little bit not practical basically. So 1984, Banker, Chance and Cooper adjoining one constraint in that model, and they just convert the model into the VRS assumption. VRS assumption is known as the variable returns to scale assumption, and these are the terms which is coming from the economics part. So this we are doing because we are ranking up some organization, that is a management aspects, and we are using the terminologies of the economics, and here we are doing the mathematics. So it is completely interdisciplinary. So we are saying mathematics for everyone. Yes, here we are using this mathematics for any engineering background, for you can say the economics person. We are using for the bio also. We are using here for management also. So that's in mathematics we are doing here. So later on, based on the different real life application, so models are coming. So in 2001, Tone gave the slack based measure, and in 2011, Meisel gave the new model, which is the advanced model, which having the more practical applicability of the model DA specifically. So I'm just giving what is the DA. We starting with the bilkul, you can say with the very basic, so that a layman can understand. We are just taking okay, as we are comparing the data, we make the data, we make the envelopment on the data. So how we can do it? Because it is a very surfacically word which we are saying we are having the data, we are making the envelope. How we can do it? What is the mathematics behind it? So we are starting from that. We are taking a very simple example, one engineering college, and having the one input and one output. Simple, we are taking a simple example for that. One input, we are saying, okay, how many numbers of teachers specifically, and how many students placed internationally. Okay, so that's we are taking the data, and based on data, we are making this table. So first, there are 4 DMUs we are taking. DMUs means what? 4 institutes, engineering colleges. Then second column will show the number input, that is number of teachers. Third column shows the output, that number of students placed internationally. So this is the data we are collecting from 4 institutes. Now we are finding the output upon input as the ratio analysis is doing. Okay, so based on the ratio analysis, we just find out the efficiency and productivity based, which is what, output upon input. So simply we can just say 18 by 86, so 0.209, and this is our efficiency score. So we can just doing the ratio analysis only, and we can find out, okay, this is the our efficiency, productivity. Now what we are doing, we are finding the relative, because we are making the surface on the data. So what we are doing, the maximum one will become the 100%, and we divide for all by that maximum, so that will give the relative value. So that is giving the relative efficiency. So you can see here the maximum is 0.209. So that's why A is the efficient one, having the 100% efficiency, relative efficiency. And we can say the B, that is the value is 0.091. So we can say the 43.4% efficient with comparison to the A here, because here A is the maximum one. So that is okay. We a single input, single output, we can apply the ratio analysis. So this is the, we can just draw the graph, and we can find out that A is on the graph, B is far from the graph, you can say it is very down, and C and D, like this one. Now we are increasing the inputs. So first input was number of teachers, second is number of students registered in that particular institute, and then output is number of students placed internationally. So at a time, if we are taking the first input, then okay, A was efficient. But if we are talking about the second input, so C is the efficient, because their efficiency, the output upon input is coming 0.1077, which is the highest one. So what, if in the ranking purpose, what we are saying, A or C, which is the best one? So we have to find out the frontier for that. Okay, because at a time A is not best in comparison to the number of students registered, but C is the best one, but A is the best one for the number of teachers accordingly. Okay, so for that we are doing the frontier analysis. We are making a graph, and we can say A and C are on the graph, and then we can just draw a horizontal line and vertical line parallel to the axes, and we can say these two are on the frontier and other are not on frontier, and accordingly we can just draw a line joining the origin to that particular unit, and then we can say, okay, how far it is from our frontier. So this graph is known as the frontier analysis basically. Okay, but again in this one it is very difficult to find out if there are multiple inputs. So if we are talking about the multiple inputs, we are saying here any academic institutes, if we are talking about, so having so many inputs and so many outputs. So here we are generalized all the things. We are not using graphically thing here, because M inputs we are taking and S outputs we are producing by using the M inputs. So at the time we are using the DEA, and we are just taking the our N DMUs. DMUs what? Organizations. So we can just use it XIK, which are the inputs, and we denote XIK means ith input of the kth DMU, and YRK denotes the rth output of the kth DMU. So now from here we are starting our mathematics part basically. So in this one, what we are saying, we are just doing the same. Efficiency is equal to output upon input. But here what we are doing, we just calculate the virtual input and virtual output. Virtual input is means what? We just take the weighted sum of all inputs. And similarly, we can calculate the virtual output, that is known as the virtual weighted sum of all outputs. And now what is the weights? So this is the important question, that which weight we are giving to that particular input. So it is again based on the experts. No, here we are not doing this. In the linear programming problem, we are trying to find out these weights. So automatically these weights are coming, so that we can say our efficiency should be maximization. So our concept is efficiency is equal to output upon input. So here it will become virtual output upon virtual input. Okay, so that is very much clear. Now, after that, what we are saying, we are finding the relative efficiency. How we can find out the relative efficiency? We just take maximum one as 100% and all others should be between 0 to 100%. So what we are doing by using these weights, what is the efficiency of other DMUs? And these efficiencies should be between 0 and 1. Because here we are not taking 100%. We are taking the value. Okay, value is between 0 and 1. So at a time we are saying it is between 0 and 1. So we are making this CCR ratio model. So ratio, because here you can see it is a fractional modeling, and why it is known as CCR? By giving the name of the scientist, Charles Cooper and Rhodes. It is introduced in 1978, as I told you. So we are maximizing the efficiency. This is the objective function of the linear programming problem. That is the weighted output upon weighted input, subject to the constraint that based using the same weights, we are finding the efficiency of other DMUs, and that should be between 0 and 1. And here, what is we are trying to find out? The weights. So that the max efficiency of that particular DMU should be maximum. That is our aim here. So the weights are the variable URK and VIK, which are greater than equal to 0. Clear? So this is a fractional programming problem. It is very difficult to solve it because we don't have any such method to solve this problem. So what we are doing, we just convert this problem into the linear programming problem, which is very easy to solve. So what we will do, there are two methods basically. We normalize the denominator or we normalize the numerator. So what we will do here, we normalize the denominator here, that is the virtual input is equal to 1. So denominator will become 1 and we are just maximize our numerator specifically, and constraint are the equation which can convert into a linear form very easily. So it will become like this one. So here this was the denominator which we are putting is equal to 1, and 1 we are taking any arbitrary value, we can take any constant just to normalize it. Okay, and we are maximize the efficiency, and we can find out efficiency in the terms of maximize of output. So that's we are doing here. We fix the input and we are trying to maximize the output. And based on that, we are trying to find out the weights so that efficiency will become maximum for that particular DMU. And for all other DMU, it should be between 0 and 1. It may be 1, it may be 0 and 1. Okay, so that is the constraint is coming in this form from the linear one. So this has become a linear programming problem. And here URK and VIK, which is the weights, it is known as the multiplier. That's why this model is known as the CCR multiplier model, in which we are maximizing our output basically. If you are seeing this model only, so you can say we are maximizing the output where we fix our input. So in academic institutes also, what we are doing, we fix the number of inputs, that is number of students registered, number of seats means, and number of vacancies for the teachers, we fixed it. And then we are just trying to do some work so that our internationally placed student will increase. So that's the thing which we are trying to do here by using this mathematical model. Now, this is a multiplier model. So there are having the infinite solutions mathematically. So what we are doing, we are just finding the dual of it. So that is the duality theory we are applying here of optimization of linear programming problem. And we just find out the dual of this model that is known as the CCR envelopment model. CCR envelopment model means this model will give you the frontier, the surface as a lambdas. So here the variables are lambdas, which will provide you the surface of the data, which will provide you the frontier. And based on that one, you can find out that which is our benchmark, which are efficient one, which are not efficient one. So if you have several inputs and outputs, you have several DMUs, then you can apply this method. Here we are minimizing our theta k, and theta k is looking efficiency. So first instance, it is showing like, okay, we are trying to minimize the efficiency, but this is not the case here because this is the dual of the efficiency score. And we know in the linear programming problem that dual having the same optimal value is the same. for the primal and the dual. So same thing, the theta k is coming here. That is like a efficiency score which we are trying to maximize. But because of the duality theory, it is look like a minimization basically. And here, this first constraint is corresponding to the output of each DMUs, and the second constraint is corresponding to the input variables, and then lambda jk, which is our you can say the intensity variable for each DMUs, that how far it is from the frontier. So that is greater than equal to 0. So here we are trying to find out this lambda jk so that we can make the frontier basically. And because of the mathematics of the duality, we can say theta k is unrestricted in sign. So if you are seeing practically, theta k is what? The efficiency score. And it is always between 0 and 1. But mathematically, by the theorem of the duality, we can't say that theta k is coming between 0 and 1. Okay, so here in the model, it is because mathematics show that it is unrestricted in sign. But practically and physically, theta k always coming between 0 and 1. That is coming from the previous model that we have done in the CCR ratio model. So it is coming always between 0 and 1 here. But we can't write it here because it is unrestricted in sign of the because of the LPP theory basically. So this model is known as the CCR envelopment model, which will provide the benchmark for each DMU by using the lambda jk. It will also show the slacks because it is a constraint with less than equal to the sign and greater than equal to the sign. It will give the slacks and surplus, and which will provide you the scope of improvement to become an equal value. If it is become equal value, then you are efficient one. Slacks are 0. So that is slacks we can find out, which is the giving you the scope of improvement as well. So that, okay, we are not doing well in this number of teachers, so it means we have to increase it or we have to decrease it. Sorry. So this is the envelopment model, and it is a very simple linear programming problem which we can apply and we can find out the solution. I already told these things. So the previous example we are taking, I am just giving you the mathematical form of the previous example, a single input and double output. So in this one, we can say we are trying to find out the maximum of efficiency, and with the V and U, these are the weights, and we are trying to find out these weights basically. But the efficiency of all DMUs EA, EB, EC, ED are coming between 0 and 1 here. And when we are just making it into the single input and two input and single output, so it will become this type of linear programming problem. We convert into the linear programming problem. It has become like this one, very simple linear programming problem which we can solve manually, as well as we can use any software to solve it. Even we can solve this by the Excel solver as well, and we can use the several software which is providing you the solution of the linear programming problem. Even nowadays, DEA solvers also having their own type of software where you just give the data and they will give you the ranking of all DMUs basically. The all linear programming they solved internally. This is the dual model. Here you can see the same data we are giving. So minimization of theta A, it means what? We are trying to find out the efficiency of the ADMU, and the first constraint is corresponding to the first output. Second constraint is corresponding to the first input, and third constraint is corresponding to the second input. So 2 inputs, 1 output, only 3 constraints we have, and we can solve it very easily, where we can say lambda AA, lambda BA, lambda CA, and lambda DA are greater than equal to 0. That is the condition of the linear programming problem, and theta A is unrestricted in sign. And as I told you, practically it is between 0 and 1. So when we are finding the value, minimum of theta A is equal 1. So if you see in the frontier analysis, A was on frontier. So that efficiency is become 1. So A is efficient 1. So now you can say it is efficient 1. So lambda AA is equal to 1 and all slacks are become 0. That's why we are saying there is no scope of improvement. It is the best one. If we are doing the theta b, so theta b is coming 0.434. So if you remember, that is 0.434, and at a time lambda AB is coming some value. It means A having its pair, the benchmark, and some slacks are also coming in some inputs and outputs, and accordingly they will show you the scope of improvement basically. So here this is a theta B, and here we are just saying the returns to scale. So in economics, this model is very good, but if you are saying that some institutes are very big and some institutes are very small, so how you can compare it? For a one university, for example, if we are talking about in the Jaipur, can you compare the JACRC with the Rajasthan University? Not. It is not possible at all, because the size, because University of Rajasthan was very old, so many colleges are there. So JCRC is a new established, and there is some colleges. Okay, so we can't compare it because of their size. It's very big and it's very small. So that is the concept of the returns of scale. So if we increase the input, we are double the input, so output is also coming double. So it means it's a constant returns to scale. They are going in an optimized scale point. But when we are just saying about the if we are increasing the input, and in the same proportionate, the output is not coming. So at the time, it is a scale inefficiency in that one. So how to find out? Based on that variable returns to scale. So there are three types of returns to scale: constant, increasing, and decreasing. So that concept is given by 1984 in by banker Chance and Cooper. That variable returns to scale is introduced in the CCR model by adjoining this convexity constraint. That is summation of lambda jk is equal to 1, which is known as the intensity variable. So it will say if the value summation is equal to 1, and if it is coming values of lambda jk is less than 1, so it is increasing. If coming greater than 1, then it is coming decreasing. So here we are saying this is the frontier. So CRS is a straight line, but VRS is the different type of frontier, and which is more closer to the our DMUs basically. So that is concept is known as the variable returns to scale, and this is given by Banker, Chance and Cooper. That's why this model is also known as the BCC model, and it is introduced in 1984. So it include the our scale efficiency, and which is can be calculated by the CCR efficiency upon BCC efficiency. And you know, by the frontier you can see, or you can visualize that BCC efficiency always be more than CCR. So at a time, scale efficiency always coming between 0 and 1. So in this one, scale efficiency is between 0 and 1, and it is more closer to 1. So it means they are just doing scale size is good here. But if it is very closer to 0, it means there is a problem of the scale size. The firm is very small or the firm is very large actually, which we have to take care. We are not just doing by the inputs and outputs only. We have to do some scale size also. We have to do the improvement in the scale size of that firm so that they can become efficient actually. Similarly, the concept of slacks is coming here. So due to the slack of that, we are just using this model, which is the we can say the slacks are included in the objective function also. So constraints are same, only the objective function is changed, and in this objective function, slacks are coming into the picture. So the effect of slacks is also coming to in the find out the efficiency score. So this is the dual of NSM, and you can say here in the last two constraints that will show you that URK and VIK. So initially it was greater than equal to 0, and somewhere it is equal to 0, which is impossible for the practical aspects. So but here it is never be 0. So it means that is practically possible values, which is we can say significant physical values basically we can find. Now the topic was the application of DEA. So we are just defining here is this small because I think there is a time constraint as well. So because of that, I will just give you the brief review of that application of that, but in the real life, because we have done so much mathematics here, we have done so many physically things, but how we can apply this into the real life application. So first I will tell you about the public transport sector. So most of the persons knows about the roadways buses. So here we are talking about the state transport undertakings, the roadways buses. So Rajasthan having their own roadways, UP has their own roadways, Bihar has their own roadways. So we can compare it. The Delhi also having their own one. So we are just rank them that which roadways is doing well, performing well, and which are not doing well, they are not doing well, and where is the scope of improvement in that one. So it is a completely real life application, real life data. So if we are using the public transport sector, which is divided into the three parts: road transport, rail transport, air transport. So we are taking the road transport because we are taking the roadways buses here, and in this one we are just taking the passenger road transport, in which you can say the public and private, but we are talking about the public because here roadway transport is a public transport sector. It is a, we can say, the non-profitable organization, because roadways buses can't be stopped. Okay, this route is not giving the profit, so we can stop it. No, we can't do it. They are just in the Rajasthan, they are just going in the Thar desert also, just to connect the small towns specifically. So we are just doing that one. So here we are taking 24 STUs data, which is we are collecting from the Central Institute of Road Transport, CIRT Pune, and we have taken the period from the 2009-2010 data. It is a very old data which we are collecting, and we are finding the values here. Inputs and outputs we are taking here, 3 inputs and 1 output we are taking. Fleet size and how many numbers in that particular roadways, total staff, and the fuel consumption per year. So this is the annual data we are taking, and the output we are taking, that is the passenger kilometer, that how many passengers are traveling, how many kilometers. So it is a composite index, basically number of passengers with number of kilometers as well. So, and in this one, we are using the categorical DMUs. What is the meaning of categorical DMUs? Because some are in the operating in the rural areas, some are in the urban areas, some are in the hilly areas. So hilly areas, there is so many disadvantages. So we can't compare the hilly areas with the rural areas, which are operating in a simple, for example, Jaipur to Alwar, Jaipur to Jodhpur, we can't compare, which are going in the hilly areas specifically. So at a time we have to categorize into the 3 parts, and accordingly we can apply the categorical model. As we know that several models are coming into the picture according to the application. So here we are applying the categorical model, and we can find out this efficiency score. So we can find out only 3 STUs are become efficient one out of 24, and the mean of is 0.658 of the efficiency score, and in which we can find out the efficiency score of each STU, and we can also find out the scope of improvement of each STU here. Similarly, the second is healthcare sector. So we are taking here the government hospitals in Uttaranchal. And why we are taking the Uttaranchal here, you can, I believe that you know very well about the Uttaranchal, Uttarakhand state, that is in a hilly areas specifically. So some government hospitals are in very disadvantageous condition, where the weather condition are worst. So at a time we have to just, they are referred to the Dehradun, they are coming to the Haridwar, they are coming to the Rudraprayag, to the lower level, so that they can refer to the patients for proper treatment basically. So here we can just take the 28 government hospitals, and there are 3 inputs and 2 outputs we consider, and accordingly we can find out this efficiency score. So you can find out the maximum scale efficiency also we find out, and we can find out that 9 government hospitals are efficient one. Okay, so they are doing very well, but other are not doing very well, and there is a scope of improvement to become a efficient one specifically. So this is, we can also find out that how many hospitals are in the increasing returns to scale, means they are very small units basically. Some remaining 10 are the DRS, means decreasing returns to scale, means they are very large, which is not required at all basically. So much staff is there. Next is education sector in India basically. So we are taking the one institute. Due to the some confidentiality, actually I just discussed with the VC of that institute, director of that institute basically. So the name of institute we are not giving, because this data is we are taken as a research purpose only. So they denied to just give the name of that institute. The data is provided but not the name. So we are just taking the 12 departments of that institute by the data of the annual reports of institute, and in that one we are finding the different type of inputs and outputs, and accordingly we can find out. For example, we are taking a simple academic higher education institute, so we are going for the placement as well, we are saying for the research as well, how was the teaching. So that we are just finding by using the different combination of inputs and outputs basically. So in this one, staff we are taking, so there are several type of staff, so we can't take all as one, because there are some professors also, some are lecturers also, some are associate professors also, staff, so PNEs also be there. Okay, so at a time we can't just convert use as one, so we are just dividing into the academic staff, non-academic staff, and we are giving the composite index for them. Similarly for staff is 1 academic staff and 0.7 is non-academic staff. Similarly the students, different type of students the institute have, just like a PhD students, postgraduate students, undergraduate students. So we are not giving some one for all students. So we are using the composite index for that. Similarly, the placement progress. Then teaching hour, because professors are just giving the time to the thesis students also. So that is not the same as the classroom teaching, because in the thesis time they are giving the time to one or student only, but in the classroom they are just teaching to the 70 students as well. So that's why we are just dividing the teaching hours for the professor, associate professor and others by using the composite index. And similarly the research index, because some papers are published in a Scopus index, SCI index, and some are in a very general type of papers. So some are conferences, and some are very good conferences, and some are not, like a tier 1 conference, tier 2 conference, or some are very simple type of a conferences. So we can't compare them, that we are not saying that okay all are one. So we are giving the some weights for that, for the composite index to make the publications basically. So we are making a research index based on the complete publications based. So we can find out these 12 departments, and these are the efficiency scores overall. But we can also find out the UG studies, we can also find out the performance of research only, because if you are thinking, if you want to go as a PhD student, you are thinking about the research only. How is the research in that particular institute, in that particular department. So we are just finding the research performance. We are also finding only the teaching performance, because the UG students are coming for teaching only. What is the placement only? Okay, so that's we are finding by the different research index basically different performance index we are finding, and then we can compare it, we can rank them specifically. So these are the some references. Due to the some time constraint, because I know that I am just going beyond my time, I am taking the time of other speakers also. So that's why I just give the brief of real life application, that here we are doing so many real life application. For example, we are doing the ranking of oil refineries, because nowadays oil is a very crucial thing we can say. We are trying to find out the supplier selection, because nowadays everywhere there is a outsourcing. So we are just using the supplier, which supplier we have to choose. Green supplier we have to choose, because environmental impact is very important here. Regulations we have to check. So every time we are just taking a different application, and accordingly we are making a different model based on that real life application. So these are the some references I used here for this specific presentation. This is actually, I just want to share for you, because you are just doing a DA here. You know a little bit about the DA, at least you heard about the data development analysis, and there are two milestones, starting milestones, the Chance, Cooper and Rhodes, and second was the Banker, Chance and Cooper BCC model. So it's a very sad news actually, because the Professor Banker, which was in USA, Temple University, so he was not more, he was no more in 1st March, actually he died. So he was very brilliant researchers in this one, in this area specifically. So that is a very sad news. I just got a last week about him, because he is a very good collaborator all over India, and they are just collaborating to each country actually. And basically he was Indian initially here. Actually his forefather is from India, from Gandhiji side, and Gandhiji gave his forefather the name is Banker, because they were the just what we can say, the Munimji of that Gandhiji. So that's why they gave the name is Banker. So this is not the surname because of the caste. The name is because Gandhiji gave his forefather to name is Banker. That okay, you are working like a bank. So that's why the name is coming Banker. So his forefather is from India. So, and he was in USA, Temple University, Philadelphia, but because of sudden illness, so he was not here. So that was a very bad news for us about the DEA specifically. So these are some references. Any questions? Open discussions. You please unmute and then ask questions. If you have any queries, anything. I was trying to relate to each person and first year students also, because they know the LPP, so they can say ki our mathematics is also using in a real life thing actually. This is for everyone, because everyone is ranking in their mind based on perception or by using the data. But everyone has to do the ranking.
Yes, ma'am.
So you can ask any question, any, it's open for all. No questions. Okay, thank you.
Thank you, ma'am.
Now I would like to request Dr. Vishal Saxena sir for giving a vote of thanks to ma'am.
Thank you.
Thank you, ma'am. Am I audible?
Yes, sir.
A very good afternoon to all. It's my privilege to have been asked to propose a vote of thanks on behalf of JCRC family. I, Dr. Vishal Saxena, on behalf of JCRC family, a very hearty vote of thanks to Dr. Shivi Agrawal, ma'am. Thank you, ma'am, for your guidance, and definitely our participants learned a lot from today's session. Your talk on application of data and development analysis will help many researchers and academicians in improvising their work and find new awareness in this direction. Thank you, ma'am, for your enlightening session and guidance.
Thank you.
Thank you, ma'am. I would like to express our deep sense of gratefulness and professionally thank the Honorable Vice Chairperson of the JCRC Foundation, Mr. Arpit Agarwal, and Principal Professor V.K. Chamna for their illuminating guidance and eternal support. I would also like to extend my humble gratitude to Dr. Ruchi Mathur ma'am and Dr. Barkha Srivastava ma'am, who guided us with their experience and also provided their inspirational concrete advice. I would like to express my sincere thanks to the team members. Special thanks to Dr. Sarita ma'am, Dr. Sarti Gupta ma'am, and other faculty and staff members for their tireless efforts. Once again, a big thank to everyone whose contribution has made this event successful. Thank you all.
I also want to thank JCRC team, a very good initiative and very good symposium. And to my thanks to the principal, Professor V.K. Chanda, and the chairperson for this symposium, Professor Ruchi Mathur and Professor Barkha Srivastav, and the convener of the symposium, Dr. Sarita Punia and Dr. Trapti Gupta, for a very great event and for inviting me for this talk so that I can extend my research area to elaborate research area to among the youngsters specifically, so that they can motivate to do the research that mathematics, yes, they are not doing only mathematics, they are just doing the mathematics for everyone. Thank you all.
Thank
Thank you,
you.
ma'am. Thank you so much. Right now, we don't have any questions. We noted down everything, and whenever we'll work upon it, we'll get back to you and with several questions.
Yeah, sure. Every time it is open for any time for everyone. Thank you.
Thank you so much, ma'am.
I request Mansavi to please give Momentum certificate to ma'am as a token of gratitude and remembrance on behalf of JCRC Foundation.
Thank you.
Ma'am, please accept this as a token of appreciation.
I accepted it. Thank you so much about
Thank you, ma'am.
you take
Thank you
your
for the
picture
talk,
and
ma'am.
just share with me.
Ma'am, I'll just share individual with you.
Sure. Thank you so much.
Okay.
Okay, thank you. So I'm leaving.
Okay. Thank you, ma'am.
The next speaker, I think that he is waiting. Thank you.
Thank you, ma'am.
Thank you so much, ma'am.
Thank you.
Shall we start the next session with Luk
Yes,
Mathur,
ma'am,
sir?
for sure.
Trilok sir.
Yes, Sumita. Just 3 minutes. I'm just downloading the presentation.
Okay, sir.
Yes.
Okay.
Okay, sir.
My slides, my screen is visible.
Yes, sir.
I request Dr. Tripti Gupta ma'am to kindly welcome Dr. Trilok Mathur sir.
Good afternoon to one and all present here, and welcome to International Mathematics Symposium. I am honored. In fact, I must say I am deeply honored, as Lok sir was senior to me. I am honored to introduce our distinguished guest speaker, Dr. Trilok Mathur, who has graciously agreed to share his expertise with us today. Dr. Trilok Mathur is Associate Professor at BITS Plani. He is an accomplished mathematician whose research has been contributed significantly to the field. Not only his work has been published in top-tier journals, but he was also the reviewer of the 8th International Conference on Fuzzy Systems and Data Mining. And he has also chaired sessions in the online international conferences, such as on advances in mechanics, modeling, computing, and statistics held at Department of Mathematics, BITS Plani. We are thrilled to have Sir here with us today to share his insights and findings. Dr. Mathur has extensive experience in the research field. He has been to Ivan Franco National University, Imperial College London, and the University of Malaya in Malaysia for his paper presentations. This symposium, surely I must say, is an excellent opportunity for mathematicians, researchers, and students to come together to share their ideas, discuss findings, and express new research areas. So please join me in welcoming Dr. Trilok Mathur sir. Thank you. May I now hand over to Dr. Trilok Mathur sir. Sir, welcome.
Thank you, everyone. First of all, I want to thank JECRC management and the principal of the college, Professor V.K. Chanda, for organizing such a event on a very auspicious day of International Mathematics Day. I would like to thank Chairperson Dr. Ruchi Mathur and Dr. Bakha Srivastava for inviting me on this occasion for this lecture. And I thank also Dr. Sarita Punia and Dr. Tripti Gupta, who are the convener of this workshop, for giving me this chance so that I can share my research with all of you. And thanks to all the coordinators also, because Sumedha is trying so much it's from the morning, trying my call, but because we are in BITS Pilani and here the problem of the network is there. So sorry, Sumedha, but and thank you for your cooperation so that this talk is possible. So today I'm talking on this International Mathematics Symposium, and the topic of my talk is the topic of my talk is the fractional derivatives in computer vision. So fractional derivative is basically a area of mathematics which is untouched since 1964, and recently now it has a lot of applications in mathematics or in other sciences. And computer vision is also a very latest technology, you can say, in the today's world, or you can say the future of this, you can say our civilization is totally dependent on the computer vision. You can name it in a different manner. Computer vision is one name, other name is artificial intelligence, one name is image processing, another name is neural network, so machine learning. All these are the synonyms of each other, or they have the, you can say, the applications in one in another. So basically the application of fractional derivative, which is totally a mathematical area into a area of computer vision, is a very new area in which I am going to talk. Today we are celebrating this International Mathematics Day. So some of the features I have collected through Google, that this International Mathematics Day, earlier it is known as Pi Day. And we have celebrated Pi Day in our BITS Pilani also, but at that time we are not aware of that. Now the UNESCO has decided to celebrate as the International Mathematics Day after 2019. But because of the years, you all know that we have been all the phases, you can say, passed through a very difficult phase. The whole world is passes through a difficult phase of COVID. So this event is not get so much, you can say, the publicity as it should get, but it has not been so much popularized. So now the UNESCO has decided to, you can say, our International Mathematical Union has decided to celebrate this day, and to make the awareness about this day is, I think that this is a very good initiative taken by the JECRC, because earlier I know about the Pi Day, but I am not aware of the International Mathematics Day. I am always checked when Ruchi has called me that we are going to conduct this work symposium. Then only I have checked. But it is really a very good initiative, so that we will get aware that what is the whole world is doing. So we are also, you can say, taking part in an international event today. So this is very much, we are also, we can feel a privileged, you can say, persons that we can work in this area. So this year theme is mathematics for everyone, and it is a, you can say, tradition in International Mathematics Day that every year they have a different type of themes. Most of the themes have the same types of meaning, if you can see the name of the previous themes. So my talk is also, I just want to, you can say, build my talk, or you can say develop my talk on the topic of mathematics for everyone. And as organizers have already tell me that the audience has the first year students, BTech students. So I have to take care of that, that I will not go in depth much, or you can say I will not take much mathematics into my talk, so that it will not become tasty. So this dish I have prepared for you, but I feel that you will like this mathematical dish for you, and because it has a lot of applications right now. And most of the first year students, those who have not, those who are in computer branch, definitely they will like this subject. But those who are not in the computer branch, that then also, if you are a mathematics student, or any, you can say, anywhere, if you are using some softwares, this talk is very, you can say, informative. At least if it is not useful, then it is definitely an informative talk, that how we can club two different areas of mathematics. So first I will talk about, so this is outline of my talk. So what we mean by the computer vision, and what are the different models of the neural networks which we are using, what are the network architecture, and what are the backpropagation method, and how fractional derivatives involved in backpropagation method, and one last experimental illustration which we have done. And right now we are trying to do some more experiments related to this particular area. So that I am going to talk about. So computer vision is basically is a field of artificial intelligence, or you can say the area of machine learning. So how machine learns, this is the main thing, that how a computer will see something, and when it is not only that capturing the thing, capturing work is can be done by camera, but when a robot sees something or a machine sees something, then how it will get identify that, okay, whatever object I am looking at, it is actually a, you can say, a person, or a lion, or a cat, or a dog. So how, because as soon as we will see something, we'll immediately classify that object. That right now we are looking at a screen, we are like, right now we are looking at a PowerPoint presentation. In that presentation, someone is presenting something. So all this thing we can easily analyze in our mind, but a camera cannot do that. But a computer through a particular software can do that. That if something is been, you can say, captured through a camera and sent to the computer's CPU, then it can easily identify something. So first thing is the classification problem. So in today's experimental settings, we have only done the classical, you can say, classification problem, which we are going to discuss. Another application is that, because a recent paper of our is been published in the neural networks journal, and in that journal, in that paper, what we have done, that if we have a satellite image, because satellite is looking at the earth 24 hours, and satellite is, if you can see the pictures from the satellites, they are not classified, they are only taking the pictures every time, continuously they are taking the pictures, but these pictures will not give you any information. Earth is there, because right now if you see at the moon, you can always see the moon, but can you identify some features from that moon, that right now it is looking like this, right now it is looking, every time we'll see it is looking at the same manner. Only thing is that the shadow of the earth is in a different manner, but you cannot get some information from that pictures. So to get some information from pictures, you have to zoom that picture, you have to find that where is the crops, where is cities, where is water bodies, where is you can say forest, where is your dams, where is your rivers. All this is not been clearly, you can say, seen if you look at the satellite picture. You have to further classify it. You have to further check it. And that you can do with the help of computers by enhancing the, you can say, information from the satellite pictures. So that paper we have recently been published. So if time or you can say some another opportunity we'll get, then we'll talk on that, how that work is been done. But today we'll talk about a very simple problem, that if you supply two pictures to a computer, then if it can be classified whether it is a cat or a dog. So this problem we'll talk about in this particular talk. So it is a, you can say, human, it emulates human visual, you can say, through the pattern recognition algorithms. So computer vision is basically the copying whatever we are doing as a human brain, whatever our brain is doing, and for that we are using the pattern recognition algorithms. So for that, can I स्क्रीन पे बहुत बड़ा आ रहा है इसका, इसको थोड़ा छोटा कर सकते हैं क्या, कुछ है? Yes, now it is okay. So computer vision recognition through the pattern recognition algorithm, the machine then process input images, label the objects on these images, and finds the patterns in these objects. So basically in the computer vision there are three basic steps. Number one is capturing the picture. Number two is the processing the image. Now, what is the processing of the image? First thing is that we will convert the images with the help of pixel into the matrix form or an array form. Or sometimes we have the noise in the pictures. Pictures are not clear because of clouds, because of sands, because of some other reasons, because something is moving, camera is moving. So there are a lot of reasons so that the picture is not sometimes captured clearly. So for that purpose, we have to first denoise the picture. So this is also an application of computer vision, that how to denoise a picture. So this is also a part of the processing the image. And the third part is that taking an important information out from that particular image or understanding the image. This is the part of the neural networks, which we are going to discuss today, that how neural networks will can apply to the for the pictures you can say classification. So I think that if you have done some courses in the neural network, then this is a very elementary course for you or talk for you, because neural networks. So to discuss neural networks, we'll begin with the human neurons. So this is a you can say functioning of the human neurons. So human neurons take some you can say electrical signals. These signals will pass to the nucleus of that particular neuron. Then we have some, you can say, application on that neuron or activation on that neuron, and then through this impulse direction and node of Renvier, it is go to the accent terminal, and it will become the input for some other neuron. So in our output of one neuron will become the input of the other neuron, and this is how the human brain or human neural network will work, or biological neural network will work. So how computer vision will work, computer will run this algorithm. So we'll compare this thing to the you can say simple graph theoretical representation. Here we have a node, which is our, you can consider as a nucleus. Some input are there, which is your input axons, and one output is there, which you are calling as the axon, and inputs you can through the dendrites. So all these things you will get in your nodes, and then in the node you have some application, and you will take the sum of all this inputs and take the weighted sum of all this. So this is the working of the neural network, that here we have some input signals. So these input signals are in the form of a vector. Each vector has some importance. Each entry in the vector has a, you can say, weight. We'll multiply this vector value with the weight and take this summing junction. Here we will take the computational part of processing part, and after that processing we'll compute the vector UK, and then we will apply the activation function for the different types of output layers. So this activation function are generally the mathematical functions. If you go, you can see, then activation functions are nothing but whose output are generally 0 and 1. So for example, you can use Heaviside active impulse function, you can use sigmoidal functions, you can use tan hyperbolic functions. So there are a lot of varieties of the activation functions depending upon the problem to problem. So we are taking a very simple problem. So generally the most popular activation function is the sigmoidal functions, which we are generally taking. But there are a lot of varieties of the activation functions, which is depending upon the problem to problem. And then the output of this particular neuron will become this your YK. Now this output of this neuron will become the input of the next layer, you can say neuron, or you can say the final output will become the finally output of this particular neural network system. So I hope that this picture is clear to all of you, that what is the, you can say, how the data is flowing. And it is only because this is feed forwarded neural networks. There are three types of, you can say, neural networks. Sometimes we have feed forward, feed backward also. And sometimes we have mix where the information will transform from forward to backward as well as from backward to forward also. So all types of neural network are there, but the most simpler form is the feed forward neural network. And in the mathematical form, this UK can be computed, as I have already tell you, that you can multiply the input with the weights and take the sum, then you will get this UK, and then you will get your YK with the help of activation function phi, and this theta k is your biased, or you can say your threshold values, so that you can compare that whether, because for every activation function we need a threshold value. So after a threshold value, the value will become the output will become 1, otherwise the output will become 0. So this theta k represents your threshold value or the bias, you can say, of the system, of this neural system. So there are different types of architecture in the neural network. So you can have a single layer feed forward network, in which you have a input layer and a output layer, and final output is there. So there is no other layers in this system. So then it is called a single layer feed forward network. As you can see, it is simple graph theoretic applications, that the nodes are, there are only 2 layers. One is input, and then you have the output layer. But in the practical life or in the real life, you will not encounter with the single layer. You have to do a lot of computations among them. So we required multiple forward network. And as the multi-layer for the number of layers will increase, the neural network is generally called as the deep neural network. So deep means that there are a lot of multi-layers or hidden layers in between the input and the final output. So in between input and final output, if there are multiple layers, you can see here we have this input layer, then we have a output layer, then again we have another output layer, and then we have a final layer. So this is called the hidden layer. And if the number of hidden layer is more, then we will call the neural network as a deep neural net. Neural net, in case of multi-layer neural networks, you can see that it's not necessary that every node is connected with another input node is connected with all the output node. It is possible that a particular input node can contribute only to a particular output node, not necessarily that all nodes are connected. So it is not necessarily that you can, all the nodes have a connections. So sometimes it is also possible that a multi-layer feed-forward neural network, you have the partially connected network. Because I'm discussing all these terms because we are using these terms in our experiment. Now the mathematics behind this neural networks. So in this case, you can see that we have inputs vectors. So these are y1, y2, y3, y4. These are our output of this particular layer. And we are computing with the help of this function f, which is our activation function. It is using the weights, and you can say the inputs x1, x2, x3, x4. So we will get the output of the first layer. Now we will construct a vector of output of all these vectors. So we'll get y1 as the output of the first layer as one output. Then this output will be provided as an input in the case of second layer to compute the values in the second layer. Here we are to compute y12, y22, and y32 at the second layer, and this y1 will become our input in this case. And then we'll compute our y2, and finally this y2 will help us to compute the final output, which is the y out. So this is, you can say, the mathematics behind this neural network. These functions are activation functions. As we have discussed, it can be Heaviside function, it can be sigmoidal functions, 10 hyperbolic functions that you can use. And these weights are, initially these weights are not known to us. So what neural networks will do, we will supply data every time, and we'll run this data again and again on the neural networks. And these weights will be adjusted accordingly. So the system itself will learn that what should be the weight so that we will get our desired output. So for that point of view, this weight is going to be adjusted. So learning means that how you will adjust these weights. So this is the next step, that what is the training, what we mean by the training of the neural networks. So the modifying the neural network by updating the weights or the bias and the other parameters so that we will get our desired output from the given input. So this process is called training. And in a case of training, it will take 10 epochs. It may have 16 epochs. You may use thousands of, you can say, data entries so that your neural network will get a better performance. It is depending upon your accuracy level, that how accurate you want your output or how less error you want in your neural network. So depending upon that, you can say that number of iterations will depend. So after each iteration, what neural network will do, it will adjust its weight so that error will be minimized. So this adjusting of the process, you can say the weights, is called the training or the learning of the network. Now there are two types of training. One is supervised learning and another is unsupervised learning. So supervised means that when you already know what your output is. For example, if you are filling a form for a competitive examination, and suppose that the first entry is that write your name. In place of your name, suppose you have entered your some numeric values. For example, you have entered 1, 2, 3, 4, 5 in the place of name. So immediately a pop-up message is appeared that please enter a correct name. It should not be a name. So this is what that immediately you have been instructed that what is required, what should be the correct manner. So there everything is supervised. You are supervised. You can say that system is already supervising that whether the entries are correct or not, and what should be your output is. Your output should be some alphabetical answer. It should not be a numeric answer. So this is known to us. So in that case, this type of learning or this type of you can say system process is called the supervised process. Now in case of supervised also, there are two types of learning. One is online learning and another is batch learning. So in case of online learning, as I have given you the example, that immediately you will get a response. As soon as you have given your input, you will get a response that your input is not correct or not in the right format. You have to give the correct input. So this is called online. Immediately you will get. Another way is once you will fill the form completely and submit it, someone will check it and give feedback to you that these are the errors you have done in your form and please correct these errors so that our process can be done. So in that case, a whole system, you can say input or whole type, one batch of entries you have done, and after that you will get a back, you can say message of, you can say that learning that these things you have to correct. So that type of learning is known as the batch learning. Now in case of unsupervised learning, what is unsupervised learning? In that case means you do not know, or the system does not know what should be the output. And I will give you one example here, that in our BITS planning, one professor is working on the pictures of these Shekhawati's Havelis. So Mandava is very popular now, a destination for the film city also, and for so many foreign tourists are coming to Mandava, and they are looking at the pictures of the Haveli. Or the different Havelis there, and these pictures are distorted. They are, because of time and because of you can say poor maintenance, these pictures get distorted, and lot of you can say information has been lost through these pictures. Now they have constructed a neural network algorithm, and they have supplied these pictures to the network, and network does not know which one is the correct one. So network is giving back us 3 or 4 types of you can say pictures, that if this is the input, then output could be output 1, could be output 2, could be output 3. And then we have to show these pictures to the experts or the painter, or you can say the experts, painters in the Shekhawati areas, that what it could be. And then these painters will decide that, okay, this option number 2 is more, you can say better, or option number 1 is better. So such type of learning of the network is known as unsupervised learning, because there nothing is to check that what should be the correct. Network will do some iterations, and after some iterations, a process has been done and some output is there, but you do not know whether this output is correct one or a not correct or a you can say false one. Maybe, for example, in case of classification problem, suppose that we have supplied some pictures to the network, and suppose some cats pictures are there and some dogs pictures are there, and it is classified as cats and dogs, but it does not know that what should be the, or you can say different classes are there, but whether it is correct or not, that is not known to us. So in case of unsupervised learning, we does not know what should be our actual output should be. That is not known to us. So such learning is unsupervised. But in generally we are using, because we are using back propagation methods in the problems which we are talking. So in that case, we are generally using the supervised learning for the neural networks. So what is back propagation? As I have just take this name. So this is the technique which has been introduced in 1986 when ANN weight updates rediscovered, and it is very simple in the concepts. And what does it back propagation means? That we will take the error of the, you can say, final output and the desired output. So we'll compute the error of this, and we will try to minimize this error, and in the process of the minimization of the errors, we will adjust the weight. So back propagation is simply known as BP, and in this case we will modify our weights so that this error will become minimum. Now when the maximum or minimum term is appeared in any system, so you can say or a mathematician is involved there, because now a mathematics can be involved, because you know that for a maximization problem and a minimization problem, or just previous talk you have heard about the word optimization problems, we require the calculus, because calculus is a very simplest tool to get a maximum minimum problem to settle down, because we can just compute first derivative, and if first derivative is coming out to be 0 at that point, we'll check all those points where the first derivative is coming to be 0, and then we will take the second derivative test, check that whether the second derivative is 0 at that point, then positive and negative at that point. Accordingly, we will decide whether that point is a point of maximum or minimum. So when this minimization or maximization problem has appeared, or because this is due to the backpropagation method or algorithms, in that you will have such thing. So we will minimize the error, and we'll adjust the weights accordingly so that our error can be minimized. So how this you can say algorithm works? So in this case, we'll initialize the weights, then we'll compute the output, then we will update the weights by this the formula that the new weight at the t+1th iteration is the old weight plus some changes in the weight, which is represented as delta Wij. Now we will do this process until the acceptable level of error has been occurred. So this is what the process is. This algorithm is very simple to understand. And you can see that here we will use the gradient descent methods. So gradient descent methods, that gradient is given by the partial derivative of E with respect to the partial derivative of the weights. So here it means that rate at which error changes as weight changes. So we want this error to be minimized, and we want that type of changes to be happen in the weights. So weight will be changes accordingly so that error will get minimized. So this technique we will use in the neural network so that we will get the desired output, or you can say the minimum error in the desired output. So when this partial derivative is there, now the next, which is the area of my expertise, is the fractional derivative. But just you can see that here we have a point of minima, and these are the gradients directions. So these gradient directions are accordingly so that we will reach at this point of minima, where the θ1 is, you can say, your weights, and j theta is your error. So you want this partial, because you want to finding out the minimum point of minima. So for that you want to take the derivative test, and you will put this derivatives equal to 0. You will get the values of the weights accordingly. You will decide the new weights, and then you can apply in the next iteration you will apply the new weights, which is given by this formula. Wi t+1, this is your new weight, this is your old weight, and this is the change in the weights. So this change will decided by this particular backpropagation algorithms. So training of the neural network using backpropagation algorithm, which is known as incremental mode of training. So you know this delta rule, that if error is a function of V and W, then the changes, this delta W can be computed by the eta multiplied by the partial derivative of E with respect to this partial derivative of W, where this eta is known as the learning rate. And this learning rate we are generally keeping in between 0 and 1. And you can see that if this learning rate is very small, it means that the rate of convergence is very slow. You have to do lot of iterations but then the network is your smoother, then there is no break in the network. But if this value of the learning rate is very high, then your okay, the learning is very faster, or rate of the convergence is faster, but in that case the network will become unstable, and that sometimes this network will break. So we have to take care of this point, that this eta can be adjusted accordingly, that it is not exactly 1 and it is not exactly 0. It is some number in between 0 and 1, again depending upon the number of iterations for the learning and number of iteration for the testing you will have. According to that, you have to decide the values of the eta. If the number of testing is very high or number of data points is very high, you can keep the smaller value of eta. If number of testing or data is very less, then you can keep this value of eta is nearly equal to 1. Now, this justification is not being given by the, you can say, earlier models of the backpropagation methods, that why neural networks has been able to capture the memory, because they are learning something, so they will capture it as in their memory, and when something is provided, some new data is provided to them, then they will work accordingly. So they have a memory property, or neural networks generally exhibit the memory property, but there is no mathematical justification behind that how memory property is being captured. And you can see that the integer order derivative, in the case of first order derivative, you can see that the order of the derivative in this case, if you are computing the first derivative f dash t, you can see that you are only computing the value of the function at 2 neighboring points, at t and at t minus delta t. So you are not capturing the whole impact of this function on the variable t. You are only capturing the value of the function at 2 neighboring points, and then you are computing the df dash t. So this is known as the short memory property, or the instantaneous memory property of the integer order derivative. It will not depend upon the long past history of this function. It is only depend upon the immediate performance of the system. But if we will move on to the fractional order derivative from the integer order derivative. So this is the term which is, I think, that new for the first year student, that there is a term called fractional calculus. I think that there are a lot of experts in JECRC itself, those who know about the fractional calculus and those people who are working in the area of fractional calculus. So I think that I will keep myself little bit, you can say, quick, so that I will quickly discuss about the fractional calculus. If you want to go in detail, I think that there are professors. I think that Ruchi herself is doing work in fractional calculus. Tripti is also working in the area of fractional calculus. So they can explain you what are the other definitions. But the fractional calculus means that order of derivative can be changed. Here you can see that order of derivative is 1. You can do the second order derivative. You can do the third order derivative. Similarly, you can consider integral as the negative order derivative. For example, d minus 1 is nothing but the integral order derivative. So this is what the understanding about the calculus, that if you are having an operator d, then you can have the integer power of this order d. If the power is positive, then you are talking about differential calculus. If the power is negative, then you are talking about the integral calculus. So this is what has been happened in the when the Newton and Leibniz are formulating the formulas for the calculus. At that time, they have used this notation called the notation of the fractional of the derivative d. But then in 30th September, I think that the date is 30th September 1695, and Leibniz wrote a letter to L'Hopital, and in that letter he has mentioned the symbol dn. Then L'Hopital asked the Leibniz that what happens if n equal to half. At that time, Leibniz is not been able to answer this question, but he said that right now I do not know about the answer of this question. So year is 1695 and the date is 30th September. That is known as the birth date of fractional calculus. So on 30th September, he wrote that I am not been able to give the answer right now, but one day important consequence can be drawn. And you can see today we are talking about a lot in the fractional calculus. So it is a branch which is 300 years, you can say now, or more than 300 years has been now, and it has been introduced, but it is not so much popular as the integer order calculus is there. You can see that integer order calculus we are teaching in the school level, at school +1 level. After 10th, I think that you are being introduced about the differential calculus and integral calculus. But no one is talking about fractional calculus even in the MSc courses right now. For fractional calculus, you have to do, or you have to be a researcher in the fractional calculus. Then only you will be introduced about the fractional calculus. Otherwise, in very few universities in India are taking this course even as an elective course. I think that 2-3 universities I know, there this course has been running as an elective course in the fractional calculus. So it is not so much popularized because some problems are there in the fractional calculus, because the definition which is the mathematician have been agreed, which is popularly known as Riemann-Leibel definition, has some problem. But then in 1964, Caputos came up with this new idea, and he has given a different definition for the fractional order derivative if the alpha is in between 0 and 1. If it is not equal to 0, it is not equal to 1. So order of derivative alpha, C represents here Caputo, T is representing the variable, alpha is representing the order of the derivative. So if order of the derivative is not an integer, then this definition is given by the Caputo for the values of alpha in between 0 and 1. So this type of derivative is known as Caputo derivative, and this derivative is given in 1964. So now you can just add the years in 1964. So today is 2023. So it is just around 69 years or something. Yes. So 60, 70 odd years is now when the Caputo has been introduced this, and now in last 70 years after this definition, there is a lot of applications in the fractional calculus. And this definition has another form, because you know that differentiation have a different type of formulas. So here we have another form for the Caputo derivative, which is known as Grunwald-Letnikov, you can say fractional derivative. And here this definition has a limiting form of the differentiation. You can see that this definition is in the form of integrals, this Caputo definition, and this is the form of the summation and limit form. So this is a simpler form to compute, and this is a form where the numerical differentiation can be done. So we can numerically differentiate or fractionally differentiate a particular function at a particular point. So this particular definition of Grunwald-Letnikov form is used generally for the numerical point of view. For analytical point of view, we are using the Caputo's definition. So this definition, you can easily see that you have different values of f involved, not only at one point, because r equal to 0 means you are considering the value at t, and at r equal to n, it means that you are considering the value at f0. So it is values in between 0 and t. But you are taking the values in between 0 and n, and you can take the values of r as integer from 1 to 3 up to n. So that you can easily see that by taking this sigma sign, you are capturing the value of the function not only at only 2 points, but at multiple points. This n depends upon your choice of this, you can say tau, that how much difference you want to in, or how much small intervals you want to use. So this tau is your length of the intervals which you want to choose. And depending upon this tau, you can decide this n. So you can capture the value of the function not only at 2 points, you can capture the value of the function at the multiple points. And here this meaning of this symbol is defined here by this ratio. So this is something related to the symbol of n choose r. It is similar, you can say, type of thing, but it is not exactly the n choose r or n combination permutation. I think that you now know the term NCR. So same thing is here, it is alpha choose r, but it is not exactly the alpha choose r, because alpha is not an integer here. Alpha is a number in between 0 and 1. So by this definition, you can easily compute the fractional derivatives of the function. And this fractional derivative provides a better mathematical explainability for the memory capturing property of the neural networks. Because earlier computer scientists are using neural networks, but they are not been able to answer that how neural networks has been able to capture the memories. But now we have a justification or a mathematical or a logical justification that why there is a feature of the memories involved with the fractional order derivative. So if we'll use fractional order derivative in the back propagation, then we can get a better results in the case of neural networks. So that we have been explored. So we have used this gradient, fractional gradient based algorithm, where the weight have been adjusted by this formula, where eta is known as our learning rate and alpha is the order of the derivative. Now, due to the complexity in the computations, we are generally using this fractional chain rule, which is defined as the approximated fractional chain rule. It is not exact chain rule, but because we are getting some, you can say, numerical results with this, so we are using some approximation from the fractional chain rule. So by using this fractional chain rule, you can choose this ux whose fractional derivative is known to us, and then we can easily apply this formula to compute this fractional order derivative here. So this is our you can say fractional chain rule, which we are using in the fractional derivatives in the backpropagation. Now there are certain limitations of the fractional calculus also. One thing is that by using the fractional calculus, the complexity of the problem has been increased. So we need some, you can say, good computer power to solve our problems. Then you can say that fractional derivatives is very complicated to compute. The formulas of the fractional you can say derivatives are not simple to compute. So this is another problem with the fractional calculus. Still there are some questions on the existence or on the definition of the fractional derivatives. For example, the derivative or Riemann-Leibel derivative of a constant is not coming out to be zero. Some other problems, there is no physical you can say justification, there is no geometrical justification is there for the fractional order derivative. Still we are not having such type of physics is there where we can say that what is f half represents, because f dash represent you can say velocity, f double dash represents acceleration. If you are a physics student, you can easily tell, but what is f half representing in the physical sense? So that is not been explored right now. But I think that as the, you can say, research in progress in this area, these questions also been settled down. Similarly, there is no geometrical representation still we have for the fractional calculus, because you know that if you are doing the f dash x, it is the slope of the gradient of the tangent of a particular function. But what is f half representing? So we do not have the answer of such question. But still, because we can be able to apply these, you can say, fractional derivatives in different areas. So we are hopeful that one day we will get some answers to these unanswered questions also. So some problems are there with fractional derivatives, but I think that we'll keep these problems one side, and we are looking at what are the useful part of this fractional derivative. So we'll apply this fractional derivative. So this is our main formula to adjust the weight by minimizing this error, by using the fractional order derivative with respect to the weight term. And then what is the problem? So this is our neural network part again. So this problem is the image classification problem. It is a very fundamental problem in the computer vision. And the goal is to classify an image by assigning a specific label to it. Suppose that we want a computer program which will, if you say some inputs to this program, so it will tell you that whether it is a cat or whether it is a dog. So this is the computer vision problem and classification problem. So it can easily label the photo as a cat and as a dog. Now, how to label it? So they have to extract the features. For example, the cats has a different types of eyes, while the dogs have a different types of eyes. The nose style of the dogs are different. The ears styles of the dogs are different. The hair style of the dogs are different. The overall weight and overall, you can say, the shape of the dog and the cat is different. So all these features are there in a picture, and we will want to extract these features. So for that, we are using the CNN. CNN is the convolutional neural networks, which generally use in the computer vision or the image processing problems. So what is a convolutional network? It is known as CNN or ConNet, and it is class of neural networks which is specializing in the processing data, which has a array-like or a grid-like topology. So here you can see that we will enter a matrix into a CNN in place of a vector. Earlier, you can see in case of neural networks, we are entering a vector, but now we are in, our input is not a vector, our input is a matrix. So it has a grid of images, and you can see the values of the pictures at different points. So it is, you can see when it is white, then it is 1. When it is gray, then it is 0.6. When it is black, then it is 0. So for black, if it is 0, and for white, it is 1. So for different pixels, we have different pixel values in this matrix. And this matrix is supplied to the neural network. And after this matrix is supplied, we will apply different filters on this matrix. So what is a filter? Basically, a filter is each filter is using for classification of a particular feature. For example, for capturing eyes, we have one filter. For capturing nose, we have another filter. For capturing ears, we have a different filters. For capturing hairs, we have a different filters. So when this input is there, we'll apply these filters, and we will take the convolution of these filters with this input. So this is our input, this is our kernel or the filter. We will take a convolution of these two metrics and we will get a output here. So this input array will become convert into this output array. So we will get a different or multiple outputs of this. Now out of these multiple outputs, we will apply the pooling of these outputs. So the pooling is generally just to, you can say the, it will, what it will do, it will, for example, for the different features, pooling is that we are collecting the data in a different types of pools, that this has eyes, this has ears of those cat-like things and all this. Then again on the pooling, we will again apply the, after convolution, we will again apply the pooling. On this pooling, we will again apply the, you can see in this picture, again apply this filter, and we'll again get a output. So every time this, you can say, size of the array is getting reduced, so we'll pool the data in a, you can say, multiple matrices. So this is what the convolution and pooling and the filter will do. So now this is our experimental setting which we have performed. So this is the data set which we have used is MNIST data set, in which you have various handwritten numerics. So all these are some handwritten numerics collected from, for example, 60,000 handwritten digital images. And they have another 10,000 training images for the sample for the training. So what we did that we have supplied these 60,000 handwritten digital images so that our program will identify that which digit is been written in this picture. So for that we have done this experiment, and you can easily see that these are our experimental settings. So our loss function means the error function is, we are using a cross entropy function. Cross entropy is nothing but the logarithmic of the overall errors. So that is log cross entropy function. Learning rate, I have already discussed. We have kept here, it's very slow. As you can see that number of points are very high, 60,000 are there. So we are keeping learning rate is very slow. Batch size for each, you can say iterations, we are using 256 pictures. Initial weights, for that we are using the Xavier initialization. Now what is Xavier initialization? So weights, because once you have started you can say algorithm for the neural network, in the beginning you have to given the values of the weight. Now you cannot give the values of the weight, all weight should be 0 or all weight can be 1 or all weight are 2. That is not been decided. Similarly, you cannot use the random algorithms or random numbers for initializing weight. So there should be some initialization, you can say, techniques. One of them is Xavier initialization technique that we'll discuss whenever we'll discuss in detail about the CNN. So then we'll discuss about the Xavier initialization. So this is one way of initializing the weight so that you will get the better results in less number of epochs. Similarly, the order of differentiation here we have kept in the interval of 0 to 2. So for different level of order, we have computed the errors and we have checked our results. And number of epochs we have used here 20. When you can see that our results are better, because when we are performing the experiment with integer order derivative, or when the order of the derivative is 1, then you can see that the number of epochs which is being used to get a desired result is 20, while in our case it is only 60. So number of epochs have been reduced by 20 to 16 for a non-integer value, and that's why we are saying that the fractional order derivative performing better than the integer order derivative. This is what aim of this particular experiment. So here is the result, final result, and you can see that the value for the value of alpha is 8 by 9, very close to 1, but not exactly 1. We will get the best result here. So training accuracy is around 99% and testing accuracy is around 98.5% we are getting. So this is a very good result. You can see that in compared to other orders, 14 by 9, 13 by 9, or at 1, if you compare it, then our results are better than the value of order of derivative at 1 also. So you can see that this is our better results we have obtained by using the fractional order derivative. So this is, you can say, I think that I have already taken 1 hour, complete 1 hour. So this is what we have done in this particular experiment, that we have established that the fractional order derivatives are performing better than the integer order derivatives when we are using the case of image processing or the computer vision. And second thing, that we have a better mathematical explainability for the memory property when we are using the fractional order derivative. So this is what the aim of my talk is, to establish that there are new avenues for the fractional derivatives where we can research, we can perform research, because in Rajasthan, I know that there are many mathematicians, those who are working in the area of fractional calculus and its applications, but mostly they are doing on a routine type of problems. And this is a problem, or this is a new area where we can explore the knowledge of the fractional calculus, and we can explore our research also. And I hope that first year students also find it. I have not used any complicated definitions to explain, only the definition of the Caputo's derivative. You can see it is little bit complicated, but I can't change it, because definition is definition. I have to use it as it is. Otherwise, most of the things I have kept at a very basic level. And I'm hopeful that you have enjoyed this talk. So I'm stopping here. These are some future work which we have planned. Application of fractional network to the more complicated structures. The available range of fractional order right now, we have only used in the division of 9. For example, 14 by 9, 13 by 9, but we have not used all the real numbers. For example, we have only used the rational numbers. We have not used the irrational numbers. Then we have also, there are for the values of alpha, that which value of alpha will give us the best result, that is only can be obtained after the experiment. But we are not been able to develop a technique so that we can pre-decide the value of alpha, that for this particular problem, this alpha will work. That is also not known to us. And similarly, for our experiments, we can perform, because once you will get very enhanced pictures, you can use these satellite images into various type of applications. For example, surveillance of wildlife, because it is very difficult for a human being every time looking on a, you can say, in a wild area, that whether a poaching activities has been happening or not. So that you can do with the help of satellite images. You can use Google Maps. So that is also a application of satellite images, that whether there is a road or whether there is a village or whether there is a building, all these things can be classified if your pictures are classified very easily. So these are our future work planning, that in the urban development, in rural development, where should be your canals, where should be your crops, which crop is better at this weather. Weather forecasting is also an application of satellite images, you can say segmentation problems. So there are a lot of applications of this artificial neural networks. And if we are using fractional derivatives also with them, then your results are better in comparison to the integer order derivative. So with this motto, that use fractional derivative in computer vision problems, I'm stopping here. These are some references which I have used for this particular talk. And if you have any suggestion and questions, then you are welcome.
Sir, I want to ask one question, sir.
Bolo.
Sir, as I'm very new in neural network, so sir, I want to know a very basic question. What is the criteria of selecting activation function? Can we take any function as activation function?
It is depending upon your problem type. Whether you are using a discrete data, then you can use Heaviside functions also. But then you have to change abruptly from 0 to 1. Or if you are using a continuous distribution, then you can use sigmoidal function, because then your transformation from 0 to 1 is smooth. So it is depending upon the problem to problem, whether your problem has a continuous manner or your problem has a discrete way of transformation. That is depending upon the problem. So it is not that abruptly we'll decide. We have to decide according to the problem, depending upon the problem.
We can take only Heaviside function like functions, or we can use 1F1 function or PFQ
no, there
function
are
also.
There are 10 hyperbolic function is also there for the activation function. So right now I have remembered about 10 hyperbolic function also is there. So 10 hyperbolic is there, sigmoidal is there, heaviside is there, and there are many others, not necessarily only these three. Right now I can only recall these three, but there are many ones. But that is depending upon the problems. It's not that because most of the problems which we are solving right now, this sigmoidal function is working very good. So that's why we are generally first we are try with the sigmoidal function. But if suppose that somebody want to do experiments, they can try with other also. Maybe some other function can work better than the sigmoidal function. But in most of the problems right now, this will work better.
Sir.
Good afternoon, sir.
Good afternoon.
Sir, as you have to discuss about the neural network, can we use graph theory in neural network?
Yes, that is graph. Networks are our graph. Actually, networks are
Yes.
bipartite graphs, you can see. So graph theory is also a tool, but we are not using more, you can say the concepts of the graph theory, not much we are using here. It is again
Sir,
problem.
but I know about the chromatical number. We can use a neural network. We can use the neural network with a
Chromatic
chromatical
number
number,
again, there are
and generate
networks
a
are a
new
particular type
mathematical
of
model.
graph, basically. Networks are a particular type of graph. Not all graphs you can use here. Because for example, cyclic graph we are not been able to use. Network are a particular type of graph where you have a flow of the information in one direction. So not all graph can be used as a network. Networks are a not all graphs can be considered as a network.
But we can apply the chromatical number and it become a very easier.
Yes, you can. You again we have to give a mathematical logic that why only chromatical number we will use. Why not other numbers we will use?
Yes, we can use it.
So that justification is also required now. Why only chromatical number? Why not other number? For example, why not winding number can be used? Why not a cyclic number can be used? So if you are using chromatic number and you are getting better results, you can apply. It's not, but you have to give a mathematical logic also, so that your problem will become applicable to others also. Otherwise, your problem is solved by you yourself by using this method, but it is not applicable to others.
Okay, sir.
Okay.
Good afternoon, sir.
Yes, good afternoon.
Sir, I am Yogita Punjabi, Assistant Professor in Computer Science Department.
Namaskar, ma'am.
Sir, I have a question. Sir, my problem statement is regarding stock price prediction.
Yes, we also have worked in this area.
Okay, sir.
We have a paper on,
okay.
we have a paper on stock price prediction, but we have only predicted one Google. I think Google we have chosen. In 2021, we have predicted it quite correctly. I think that we have got good result for that.
Okay, sir. So my problem statement is same, and my question is regarding you have just discussed the memory property, right?
Yes.
So can I use Caputo's fractional order derivative for long-term prediction?
Yes, we can
We
use
have two types of prediction, short-term and long-term.
In the case of numerical or neural networks case, we are using the Grunwald-Letnico definition.
Okay.
And when your time t is very small, you are taking t tends to you can say 0, or number of epochs n tends to infinity, then all these definition will merge. Caputo's definition as well as Riemann-Liouville as well as Grunwald-Letnico.
But my problem statement is related to long-term prediction, not short-term.
Yeah, you can use Caputo's derivative in that case.
Okay, sir. Thank you so much, sir.
We have used Caputo derivative for 10 years data. We have used Caputo derivative.
10 years, okay.
Yeah, for 10 years, our experiment data set we have used. So for that we have used, because we have the data for 12 years of a particular share. and we have predicted it quite, you can say we have not been able to predict the values, but we have been able to predict the trends, that whether it will go up or down, and how much up and how
Up
much
or
down.
down? In long term, yes, we can choose only.
But
We can decide only.
एग्जैक्ट प्राइसिंग में हम लोग नहीं कर
Yes.
पाए, लेकिन पैटर्न रिकॉग्निशन हम लोग कर पाए हैं उसका.
Okay, sir. Okay, sir. Thank you. And sir, one more question is, how can we decide the number of layers in neural network for our particular problem?
In convolutional, in image processing, generally 5 layers. They are again, there are different types of architectures. So in case of in case of CNN, LayNet 5 we are using. So there are 5 layers in that case.
Okay, okay, sir.
For image processing,
Okay.
but for other process, again, depending upon experiments.
So how can we decide number of layers? This is my question.
How? Because यहाँ तो standard है, हम जिस problem पे काम कर रहे हैं उसमें तो LayNet 5 ही हम use कर रहे हैं. I will see
sir.
कैसे बताएंगे इसमें how we will apply.
Sir, have you used neural network for stock price prediction?
For
Or
stock
some
price
other-
prediction, yes, our paper is there. You can Google it. In Nikita Singh, Sugandha, and myself, Shivi ma'am, and 2-3 other authors are there. So it is a paper in 2021 Journal of Physics में छपा था ये पेपर. जो उनकी कॉन्फ्रेंस सीरीज आती है ना जर्नल ऑफ फिजिक्स की, उसमें छपा है. तो 2021 का है, हमारे गूगल स्कॉलर पे आप देखेंगे तो मिल जाएगा आपको. एन सिंह.
Definitely see. Thank you, sir. Thank you. Thank you so much.
Okay.
Good afternoon, Dr. Tilok.
Good afternoon, ma'am.
This is Jyoti Thanvi here.
Namaskar, ma'am. Namaskar.
Namaste. Namaste. I know that we are bus में अच्छी हूँ. It's good.
आप बहुत दूर चले गए लेकिन.
हाँ चली गई, अभी तो खैर राजस्थान में हूँ, लेकिन I'm just wondering that you have predicted stock prices. Did you use any probabilistic models into that, or some stochastic modeling?
No, we have not used probabilistic stochastic model. We have actually, I have seen some quotes from your on Facebook that it's neural network itself is using the statistics.
Yes, that's what.
You can in some way can say that it is a stochastic process also or not, but we have used the neural network and deterministic model.
So the computation has been
Fractional
done
calculus
by.
We have used basically.
Okay, so it was a kind of theoretical work or some already inbuilt functions you have used in computation. Did you use some inbuilt functions in computation?
No. We have to make our own program for it. So we have not used inbuilt function. We have, because we are using fractional order derivative. And right now there is no inbuilt functions for the fractional order derivative. We have to create our own. We have जो student थी उसने Python सीख रखा था, तो उसको वो Python में उसने convert किया program.
Okay. But I would definitely like to look into that paper.
क्योंकि हम जो भी स्टूडेंट काम कर रही है अभी उसको पाइथन में प्रोग्राम खुद ही लिखने पड़ते हैं.
Okay, right.
So it is not available. लाइब्रेरीज में से नहीं मिलते हो.
Okay. खैर हम लोग फिर बात करेंगे.
I did a problem for this neural network. उसमें what I faced is to how to initialize weights. आपने उसका आंसर.
Initialization के लिए there are a lot of procedures. One I have given you, Xavier initialization.
But can we use any method, any problem to be specific according to the problem?
ये तो pre-decided करना बड़ा मुश्किल है, और कि पहले से ही पता हो कि कौन सा यूज करना है. You have to experiment it because data अपने पास है, कंप्यूटर अपने पास है, 1-2 बार experiment करके देखना पड़ेगा. But again, you have to write the program. You must know how to write the program and how to initialize the weights.
The main problem that I faced was to initialization of the weights.
Yeah, so again, there are 3-4, I think, initialization process right now. So try one and one another, which one will work, that you can see. But do not do randomization or random numbers, or you can say initially constant weights. That will not work.
Okay. Thank you, sir.
Thank you.
Over to you, Sumedha.
I would like to express our sincere appreciation to our esteemed speaker, Dr. Trilok Mathur sir, for enlightening us with his presence and sharing his knowledge and expertise with us. JCRC Foundation is truly privileged to have you, sir, today in this symposium. I again expressed our deepest gratitude to you, sir. Thanks a lot, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank
you, sir.
Enlightening us.
Thank you, sir.
Thank you.
In JCRC College, many faculty have been benefited today by your talk, as many of us are co-researchers. Thank you once again, sir, for the enlightenment.
Thank you. We are also looking for a collaboration. There is no, you can say, you can anytime we can contact any type of collaboration. We are already open. And I just want to advertise one thing, that if you know anybody who is already completed MSc and want to work in international PhD program, then please ask her or him to apply in our program, which is BITS RMIT PhD initialization program. And this is a very unique program in which a candidate is working not only in India with BITS planning experts, and with 1 year he will spend in Australia. RMIT is Royal Melbourne Institute of Technology, very known university in Australia. So he will spend 1 year in Australia also. So this is a collaborative program between BITS and RMIT and fully funded by both the organizations. So whenever a student is residing in India, he will get a stipend which is, you can say, better than NAC JRF. And similarly, when he or she will be in the Australia, then they will get the all expenses been covered by the Australian counterpart, and visa fees and everything will be given by the both the institutes, BITS and RMIT. So we have already advertised it. It is already on our Facebook page. And if you want to see the link also, then please just Google it, BITS RMIT. And you will see the program. There are 126 projects are there in different areas of engineering and sciences. So you can choose according to your choice. You can choose multiple also, that 2-3 programs you can choose for your research pursuit, but again, depending upon your eligibility criteria. So for our program, for our project, the eligibility criteria is MSc in mathematics, and preferred is MSc in OR. So this is one is criteria is MSc mathematics, but OR should be one of the preferred area. So that program is there. Dr. Shivi Agarwal is a supervisor. Myself is co-supervisor in Indian part, and Professor Prem Chetri and Professor Matthew is there, and they are the Australian counterpart. And we are, this particular project is on the smart cities project for the last mile logistics. So for last mile logistics, because there are a lot of problems during last mile logistics. So for that, to solve that, there is a PhD, we have proposed a project for that. And there we are using the data development analysis and multi-criteria decision-making techniques. So I just want to request all of you that please, if anybody is, because we want a very good candidate, because selection procedure is not very simple. It is not in our hand to select the candidate. We'll take the interview and we'll update the names on the portal. And then a senior committee will take the interviews of all these students, those who are on the portal. And out of 250 students, only 30 students will get chance for this particular program. So if the student is very good, then and they have an international exposure and it is already fixed and fully funded, so it is a good opportunity for a MSc student if he is looking for a research position. And 1 year Australia is also very important feature, because I have received so many calls regarding that. तो बोले कि सर हमारे को तो ऑस्ट्रेलिया जाने नहीं देंगे, ये नहीं करने देंगे. तो मैंने कहा भाई वो पहले से डिसाइड करके रखिएगा, क्योंकि वो ऑलरेडी उसका इनबिल्ट पार्ट है. You have to stay Australia for 1 year. अब कई लोगों का फोन आया, सर हमारे तो घर से ही बाहर नहीं जाने देंगे. तो फिर मैंने कहा फिर आप मत अप्लाई करिए. And it is not a part-time program; it is a full-time PhD program. So thank you, everyone.
Thank you, sir. Thank you once again.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sumeda, next session 1:30.
Yes, ma'am.
Sumedha?
Yes, ma'am.
Yes, ma'am.
I think ma'am in meeting. So shall we start?
Yes, ma'am. Good afternoon, Monita ma'am. Ma'am, please unmute.
Yeah, thank you.
Now, I would like to request Professor A.S. Shekhawat sir to kindly welcome Dr. Monita Bora ma'am.
Sumedha?
Yes, ma'am.
Professor Shekhawat sir was in leave. So I will give the welcome note of the Monita ma'am.
Yes, ma'am. Sure.
Thank you, Sumedha. Good afternoon and welcome to International Mathematics Symposium. I am honored to introduce our distinguished guest speaker to Dr. Monita Bahra ma'am, who has graciously agreed to share her expertise with us today. Dr. Monita Bahra, a senior academics with a rich teaching experience for almost 23 years. She has an international exposure of teaching in reputed universities in the United Kingdom. Currently working as an associate professor in University of Birmingham, Dubai campus. She is also the program director of MSc in Financial Mathematics. Before joining University of Birmingham, she worked as senior lecturer, program director in BSc Business Analytics, University of Exeter, United Kingdom. Prior to that, ma'am worked as lecturer in data science analytics, University of Leeds, United Kingdom. Also worked both as lecturer and assistant professor in the Department of Statistics, University of Bahrain, Kingdom of Bahrain. Dr. Monita Bahra ma'am has taught subjects which includes multidisciplinary area like data science and analytics, business analytics, mathematical and applied statistics, data science and management, biostatistics for both undergraduate and postgraduate levels. We are honored to have to ma'am. Now I would like to hand over to Dr. Monita Bahra ma'am.
Thank you very much, Dr. Sarita, for the warm
Thank
welcome.
you,
Hello, everyone, and greetings to all for International Day of Mathematics. Can I share my screen?
Yes, ma'am, you can share my your screen.
All right. So can you see my screen?
Yes.
Yes, ma'am.
Just a moment, I'll try to, yeah. So again, thank you again for the very warm welcome. So I will be talking about selecting the right model for predictive analysis. This presentation is mainly, targeted to undergraduate students with mathematics or statistics. So there might be really intellectuals present in this format, and I think that's a very simple topic, and everybody is aware of this. So selecting a model is a very important topic in data science or in statistics, or statistical theory. Okay, so this is fitting a model. So this picture looks beautiful. This is a model, and she is being fitted by a designer who's going to display and walk in the ramp. So it's, I think it's challenging for her, as you know, to fit her dresses in the proper way. So the same is with us when we are talking about statistical model. Yes, we do face problems. What is a model? So we know, according to a very famous statistician, let me quote his words: a model is a lens through which to look at your data. So it's a representation of your data. So I'm just concentrating on data science here, not much of a statistical theory. So in data science, a predictive model is a formula, and you're trying to estimate the unknown parameter, that your variable of interest is your target variable. So this is, although, you know, fitting our statistical model is not as beautiful as fitting a model in a ramp, a model walking in a ramp, but it, it is equally useful, for having the right model, selecting the right models for the accuracy of any kind of prediction. So yeah, let's go ahead. So I will be concentrating on predicting, as I have said, selecting the models for predictions or predictive analysis, which is a very important area of data science. Now, again, we know these are the very popular predictive models: linear regression, logistic regression. We do have the tree-based models like decision trees, random forests, support vector machines, others, and there are many others. Now, these are, again, very vast areas. So I'm just giving you an overview, but my concentration will be mainly on linear regression. So model selection. It's a very important and fundamental task for any scientific investigation. So we need to have the appropriate data. We need to know which model is to be fitted rightly. But we definitely have to think of selecting the appropriate model, which is a proper representation of the data that we are analyzing. Now, what is the challenge here? The challenge is, choosing one model out of a range of models, so that we are whatever results that we are, trying to predict is not misleading. Because when we are working with real life data, it's very important that we are selecting the right models. So it's the main decision is made by people like a statistical analyst, because we have some kind of skills, we have some kind of training to decide which model we are going to use. So, for example, we are working with historical data. We know that we are going to use, time series model, or if you're working with some kind of, regression, we're trying to estimate some kind of an outcome variable, we use a regression. So it's basically to the statistical analyst. But again, even though we are having the decision to know which model to do, we still have to make further choices about the model structure, especially what kind of features we need to select in the model. So in data science, the two main classes of model selections are probabilistic measures and resampling measures. So probabilistic measures, I will be discussing, it's a matrix actually, and based on the matrix, we decide, okay, this is the right model. And again, resampling measure is based on data. So we use data to decide on selecting a model. So we'll discuss this later in our slides. Just to mention here that, since my topic is not, I'm just giving you an overview, it might not go around for 1 hour, so I may just finish in 30 minutes. Okay, I think that is not a problem. Have you heard about, or have you seen this, this Anscombe's quadrant? Are you familiar with this? I think most of you will be familiar with the Anscombe's quadrant, where we are trying to looking at an exploratory model selection. So if you look at this 4 graphs, there has been linear regression or a linear model done here. But we do see that although these are very close to a linear model, these two data sets are not linear, but a linear model has been fitted here. But that's not the right. So it's not, if you are trying to do some kind of, prediction based on these two models, your results will be misleading. And if it is a scientific investigation, it is harmful. So if this Anscombe quadrant, these results or these displays are from these 4 data sets. If you notice, these 4 data sets are very similar. Yeah, and so we can think of doing a regression model for a linear model for these 4 data sets. But what we notice that the second data set and the 4 data sets are not linear. So again, if you're using this for some kind of scientific investigation, this is going to be misleading. So that's an example where, model selection is necessary. It's not just, oh, this is the model, I'm going to do regression. That might not work. So feature selection. So it's very important, to select the right features in a model. So my concentration, as I have told you, will be just looking at the regression model, because the later models, again, it needs a lot of more in depth, and it's again a vast area, and it's a wider topic. So deciding which inputs to use in a model is described as feature selection. Why is feature selection important? It is important because it reduces the complexity of the model, it improves the accuracy of the model, and it also reduces a phenomena or situation called overfitting. So if we do not select the right features, we do encounter situations like underfitting, where we do see this model is not closely representing our data. We do observe a situation or phenomenon called overfitting, where we see that the model is trying to take every element of the data points. So in that case, it is also modeling the random noise or the error. So again, the results here will be misleading. So if we are using this model or if we are using this model, our results are not accurate. But this model is a very close representation of the data points. So these are the situations we may encounter when we are not selecting the right features in the model or we are not selecting the right model. So my concentration now again will be on overfitting. What is overfitting? So this is another example of a graph of situations where we see underfit and overfit. So we have a representation of income versus tax, and we do see a linear model, which is based on the data points here. We do see that it is not actually a close representation of the data points, while the red curve tries to capture every element of the data. And in that case, it's also modeling the error involved, the error in the data itself. So that's misleading again. So this is a very well fitted model. This looks very nice, and this linear representation is very much closer to the data point. So this is, it's fine to this model. So that's an example, just an example. Now, how do we know it's, we are overfitting or we are underfitting, and from where has this come? Now, if you are familiar or have you ever heard about Occam's razor's law of parsimony? Occam, now the word razor itself, I think, brings to your mind about a gentleman and a shaving kit with some razors. I think you're very close if you are having things like a razor. It's very close to what you're thinking or imagining. Yes, we are shaving off, we are eliminating the extra features. We do not want to be incorporated into the model. So that's how Occam's razors come. It was actually developed or founded by William Occam, and it's from the 18th century. The William Occam is a scholastic philosopher, and by the law of parsimony, it means that you only incorporate those inputs which are necessary for the model, not anything extra. So a parsimonious model is a model that accomplishes the desired level of explanation or prediction with as few predictor variables as possible. So it's not necessary that a model is very complex. It doesn't look, you have a big data set, you have a model, and you have a lot of complex features, but it's not necessary that it should be complex. It can be simple, but being simple, it has to capture all the elements or all the features of the data. So that's important. Again, in a statistical model, when we are discussing statistical theory, the goodness of it also describes how well it fits a set of observation. So anything that violates the parsimony law is overfitting. Okay, so if it's not following, it's violating this law, it is overfitting. So overfitting is a situation which violates the law of parsimony. So the problem of overfitting is a condition where the statistical model begins to describe the random error or the noise, as I've just now told, in the data, rather than looking at the relationship between the variables. So Occam's razor, again, I have spoken about this, or the principle of parsimony calls for using models and procedures that contain all that is necessary for modeling, but nothing more. So when we say, if you're having a situation of overfitting, it tries to capture every element. That means we are putting the garbage in. And if you're putting more garbage, you're producing more garbage out. So that's the outcome variable will produce more garbage out. So it's not good. So you have to be just concentrated on those variables which are enough to predicting purposes only. But we do encounter situations where we have a data set, we have a lot of variables. We do see that variables are significant, statistically significant. You can do a regression analysis, you see that this variable is coming out to be statistically significant, but it's not affecting the response variable. It's not affecting the outcome of the response variable. So that's again a problem. Although it may look statistically significant, but it's not as important. But again, when you're doing it for a proper, real world scientific investigation, it is a problem. So let me just discuss an example which I have worked in R. So I have just programmed an R output here. So this is a data presentation or a graphical presentation of a data generated through R. So if you notice that this is a quadratic, data generated, and we know, looking at the graph, we can imagine that this is a quadratic plot. So I have used R codes to do that. And what I have done is, so I've generated some data, and that's a quadratic data set. And I have created the plot here. Once done, I tried to create 3 models. So where our x1 is just the x, x2 is the x square, and x3 is the cube of the x. So I created 3 models, one with just the x, that's the linear model, one with the x2, which is the squared, and that's a quadratic model. And the third one is x2 and x3, and that goes to cubic model because the highest power here is 3. So based on these 3 models, I tried to compare the likelihood of each model evaluated at the maximum likelihood estimate parameter. So I have taken the log likelihood evaluated at the maximum likelihood estimate. So these are just used worked with programming language RStudio. So once I've determined the log likelihood for each of the models, this is again, R code. So you can just ignore the R code, just have a look at the output. And that's for the log likelihood for the linear model. This is for the quadratic model, and the log likelihood for the cubic model. So essentially what we see that the best model from here is represented by the cubic model, although it's very, very close to the quadratic model. But again, if we are using, without knowing from how the model was generated, how the data was generated, we imagine that our right model is the cubic model, but it is not. What we want is, we want our models to be as simple as possible, but again, capturing all the important features of a data set. Now, how do we avoid this? How do we mitigate overfitting? So that was a situation of overfitting. That was an example of overfitting where if we hadn't known about the data, we would have used the cubic model because that's what's the best estimate is coming out to be. And if we do so, and we try to do some kind of a prediction there, it might be misleading. So in that case, we have to avoid that. And how do we mitigate or avoid overfitting? So there are, I'm just looking at 3 features here, or 3 methods here: selecting the right features, penalized likelihood method, and cross-validation. Now, I'm not going to discuss in detail the right features. I'm just going to concentrate on the penalized likelihood method and the cross-validation. In selecting the right features, when we talk about regression model, we do have the forward stepwise method and the backward stepwise method, where we eliminate features which is not necessary one by one, looking at the significance. So that's again another detailed topic which can be discussed, in depth, but I'm not going to look at this now. I'm going to talk about the penalized likelihood method and the cross-validation. Penalized likelihood method is the probabilistic measure which we discussed in the beginning, and the cross-validation is the resampling method. So model selection by penalized likelihood, what does it do? It improves on the previous maximum likelihood. So it will penalize the extra parameters that we are estimating through it. So it uses maximum likelihood method. And then, so that's what it does. It penalizes the extreme estimates, and it therefore thus corrects overfitting. So this is the general algorithm or the metric used in penalized likelihood. But there are different, information criteria under penalized likelihood. The two most popular is the AIC and the BIC. That's the Akaike information criteria and the Bayesian information criteria. So these are information criteria approaches used to assess model fit while penalizing the number of estimated parameters. So we can apply this. They're most popularly used in data science, and then you can decide on selecting the right model. So AIC, or the Akaike information criteria, is named after the developer Hirotugu Akaike, and this is the metric used for finding out the AIC. L star here denotes the likelihood function. K is some arbitrary constant, and we can there is a particular value for that, which we can choose the K. And then we choose the model which gives us the smallest AIC. So we have decided which model we are going. So we are going to do a regression model. We have a number of models out of this with a number of features, and then based on the AIC, we are going to say, okay, this is model will be the right model for our prediction. Similarly, we have the Squarce Bayesian criterion, which was again developed by Squarce. This is the metric used again here. This is the log likelihood here, the maximum likelihood. So again, we select the one which has the lowest BIC among the different candidate models. We do have another metric, or penalized likelihood method, which is not an information criteria, but it's a Wilks theorem. And this is used to decide if the likelihood difference between two models is statistically significant. And this is generally applied when one model is nested in the other. So that's how it works for how Wilks theorems works for penalizing or selecting the model. And cross-validation. The next one is the resampling method, which is the cross-validation method. This is a popular, very popular method used in data science, machine learning. So how what we do is we build the model, we fit the model, and we try to test it in an unseen data. So that's how this cross-validation works. So it's an alternative method for avoiding problems of overfitting and to see and to know how well a model can predict unknown or unseen data. So cross-validation, we have a few steps which needs to be followed. We have the data set, and then we divide our data set into two subsets. So one of the data sets is the training data and the other as test data. So the training data, say we can split it in as 80%, 20%. So 80% is training data and 20% is the test data. So we try to build our model in the training data. We try to estimate the parameters in our training data. We can also take 70%, 30%. And then we try to test it and validate it on our test data. So we use the training data to fit the statistical model and then learn and estimate the parameters of that model. We use the fitted model to predict the outputs of the test data and based on the inputs of the test data. So we use the model, whatever we have estimated, we'll try to predict it on our test or unseen data. Then we'll try to evaluate the accuracy of this prediction. So it's one split might not work, so you have to do a number of splits of the data. So you repeat the process with, again, say 2 new data subsets, and you can keep on repeating this. You can iterate this process a number of times, potentially repeat the process with 2 new data subsets. So, but again, 2 new data subsets may be also not sufficient. We can keep it, iterate it a number of times. So generally, we need quite a few cross-validation data splits before we can be confident to select the right model. So the most commonly used is the k-fold cross-validation. So then we have 10-fold when we are trying to do splits 10 times. So you can have this is again a vast area. Again, this is just one talk is not sufficient, to know more about cross-validation techniques or the penalized likelihood techniques. So that's this is a visual representation of how the k-fold cross-validation works. And this picture is taken from the website medium.com. It's not something that I have drawn or I know. So it's taken from there. So we iterate this. It's the first 20% we've taken the test data, and the remaining 80% we have taken as the training data. So we'll try to model or build our model, fit our model in this training data, and then I will try to predict and estimate the parameters as well. And we'll try to do the prediction in this test data. Similarly, we then again take a second iteration where we take the second 20% of our data as test data and the remaining 80% as our training data. We repeat this as and so on till the number of folds you want to do, say 10 folds. So you repeat till your 10. So you'll split the data into the 10 folds in 20% or 80% or 30% or 70% test and training. But again, this is a large area of research or discussion which you can do further on. I would just like to do a simple example, just understand what is the penalized likelihood method with very simple understanding, because if I know there are undergraduate students here, and I use this example, in one of my lectures as well. So I think you will find it helpful. So we have a data set where we have the medal counts of this is a real data set actually for the medal counts of 2008 in the Olympic Games, 2012. I know it's not visible well, but the screenshot taken of the data in my spreadsheet. Then my medal count in 2016. We have two variables here, GDP and population, and we are trying to predict the medal counts in the future Olympic Games. So I'm using medal 2016 for this regression modeling as our response model. Okay, so we tried to see there are two features here, and let me create three models here. We create first model with trying to predict the medal count with just population as the predictor variable, and this is a very common regression model, linear regression model. Then we try to do a second model with only GDP as the predictor variable and try to predict the model medal count. And we take another model with both GDP and the population to predict the medal count. So we have three models here. I'm not going to present the regression analysis here. I'm just looking at which model will be the right one to select. So I'm applying penalized likelihood method as well as the cross-validation. Now I have worked this in R, so I will not have the output all of them, but it's just a simple penalized likelihood what we have done using R. So this is by the penalized likelihood method, and I have used AIC, Akaike information criteria. So I tried to find out the model errors via AIC. So this is the first model with the population only as a predictor variable. This is the second model with GDP only as a second the predictor variable, and GDP plus population as in the third model. So what we notice here is the model with GDP only is the lowest AIC, and we can we can consider now that the second model is sufficient enough to predict the model count. So our second model was this model with only GDP. So I think even if we just think without the statistics, I think population is not a necessary feature to predict how the medal counts will be for a particular country's winning medal count in forthcoming Olympic Games. So I think GDP may be sufficient. How developed a country is based on that. How much of effort is given to sports in that country. How much of funding is there, or how much development is have been made progress in sports sector. So that may be a sufficient predictor variable for doing this kind of prediction. So I just wanted to confirm this, whether my analysis was correct. So whether I should select this, I just tried to do a cross-validation as well. So I did cross-validation. I just did one split here because I did not want to do it again and again. And since I have done already a penalized likelihood method, and I noticed that, yes, I calculated the mean squared errors from the cross-validation, and I seen that the GDP only model, that's the second model, is also giving us the lowest mean squared errors. So we can confirm that, yes, to predict the medal, winning a country's medal winning in Olympic Games, GDP is the sufficient feature to do this kind of prediction. So that's how that's the core motive of this talk, or the core focus of this talk, that how and why we need to avoid overfitting, and why we need to select the right model so that we do not have any misleading outcomes, and it might be harmful if you're doing really a research-based investigation or scientific investigation in the real world. Yes, so that's all. And so just a key takeaways of what we have discussed is how we can and why it's important to select a model why we need to fit the appropriate model. We discuss the problem of overfitting and how to mitigate or avoid overfitting. Now, this is just an overview which I have given you in the few minutes today that I have spoken. But if you're interested, to knowing further about all these, concepts, maybe especially, cross-validation, penalized likelihood method, and there are many more. Even if you want to learn about random forest, decision trees, classification problems, there are many things you can discuss. I have some references and further reading if you are really interested to dig in further, So please refer to these books. These are very good books, and I think this will be very helpful. And that's all, I think. Thank you for giving me an opportunity to speak and having the privilege to see you all here in JCRC. Thank you very much. I just stopped sharing my screen.
Thank you, ma'am. Now, I would like to request Mansavi to give a vote of thanks to Monita, ma'am. Mansavi, please unmute yourself.
Thank you, Monita ma'am, for enlightening us today in this symposium. The way you kept up the theme mathematics for everyone was truly insightful. Thank you for letting us know about the selection of right model for predictive analysis. I express my deeply gratitude to you, ma'am, and on the behalf of JIC Foundation. Please accept this token of great appreciation from us.
Thank you very much. Thank you. I'm very much happy. I'm very happy to be here.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah, I'm just, is it okay for me to continue with the meeting, or should I leave? I just wanted to know about this.
Sir,
no,
ma'am,
as
you
can,
wish.
As you wish, you can continue.
Okay, thank you. Thank you so much.
Okay, ma'am. Thank you, ma'am.
Thank you.
Thank you,
so
ma'am.
much.
Sumedha, now call the Jyoti, ma'am.
Good afternoon, Jyoti, ma'am.
Good afternoon, Sumedha.
I would like to request Professor UK Parikh sir to kindly welcome Dr. Jyoti Thanvi, ma'am.
Parikh sir, please unmute yourself.
Unmute.
Parikh sir, carry on.
Am I audible?
Yes, sir.
Yes, sir, you are audible.
A very good afternoon to all. It's my privilege to welcome Dr. Jyoti Thani ma'am, Associate Professor in School of Mathematics, University of Birmingham, Dubai. Ma'am is a passionate researcher and a mentor involved in teaching learning statistics for more than 2 decades. Her research interest is biostatics and public health. He worked on CVD, loved to take initiatives and teach statistics to the students coming from different disciplines. Presently working as associate professor in School of Mathematics, University of Birmingham, Dubai. Ma'am has completed PhD in statistics degree from University of Rajasthan, Jaipur in 2004. Her research and title is Prevalence of Coronary Risk Factors in Premenopausal and Postmenopausal Women, a statistical analysis from University of Rajasthan in 2004. Ma'am has presented various papers in the conferences of national and international repute and delivered invited talks and lectures at many international forums. Now I request Dr. Jyoti Thani ma'am to initiate a talk. Ma'am, please. Dr. Jyoti Thani ma'am.
Thank you, Professor Parikh, for such a nice and lovely introduction of mine. But having this kind of introduction from your old colleagues is like a kind of treat, and watching you all on the screen is like a wonderful experience.
Ma'am, welcome here.
Thank you.
Ma'am, I'm very fortunate to hear Dr. Jyoti Thwani ma'am voice after a long time. Ma'am, I'm very delighted to share, ma'am, this my views, ma'am.
Thank you very much, Professor Parekh. Good afternoon to all of you. I would like to start.
Thank you, ma'am.
With this note that I'm in India on a leave and I'm not having anything with me, not the right laptop with me. I was, and I am caught in a trap by Dr. Punia. I was not supposed to speak on anything. Anyways, it's always wonderful to interact with the student community. So I would be talking just very basic things, and then I'm open for any kind of questions would be coming from the students. Right. So I'll just take up 5-10 slides. I'll speak on them, and then I'm open to have a discussion with the students if there are any questions, right? So I'll just share my screen and start with my topic. Basically, being a statistician, my expertise in stochastic modeling, and right now I'm teaching financial mathematics. So my topic is very much related with financial mathematics and the stochastic modeling. So I'll share my screen, and then after having a quick discussion, is it visible to all of you?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am, visible.
Okay, thank you. And full screen mode is there, right?
Yes, ma'am.
Yes, ma'am.
No, ma'am. No, ma'am.
Okay.
You have to.
Is it there now, right?
Yes, ma'am.
Okay,
now it's full screen.
So, stochastic modeling and its role in financial mathematics. This is a very vast topic, and we can talk on hours and hours on this topic, because in itself, stochastic modeling is a very important tool. And when it is applied to financial mathematics, it has a lot of importance and a lot of complexities involved into it. But in the last 30 years, this field has grown like anything. An earlier time when people used to invest in finance, people used to work on their intuitions and their experience and their learning, what they have learned from their experiences. But now we do have appropriate tools and methods which can tell us that how to relate your financial decisions with a very sound mathematical background and to predict on all those things and invest in all those things. I won't be going into very much detail, but yes, I'm open for any kind of questions. So now the next is, what is stochastic modeling? What do we mean by stochastic modeling? So I'll be starting with very basic things. So a quantitative description of natural phenomena is called a mathematical model of that phenomena. When we quantify any characteristics with some of the parameters, some of the variables, so any quantitative description of a natural phenomena is a mathematical model. Now, if we talk about mathematical models, they can be deterministic, they can be stochastic as well. So a deterministic model predicts a single outcome from a given set of circumstances, and a stochastic model predicts a set of possible outcomes weighted by their likelihood or probabilities. When we take into consideration their likelihoods and their probabilities, we look at the events from probabilistic point of view, and then we apply the model, and that is known as the stochastic model. So stochastic modeling develops a mathematical or financial model to derive all possible outcomes of a given problem or a scenarios using random input variables. We have randomness in the input variables. That is very important thing, that we have considered the randomness into the input variable. I'll be talking on this after two slides. So if you look at this graph, if you look at the different colors, they are like, if you look at the different share prices every day. Suppose these are the share prices, everyday share prices, and these are the graphs for 7-day share prices. Now, if you look at this zigzag curve, that is what? Some people call it a random noise. Some people can call it Brownian motion. So using Brownian motion or the probabilistic models, if we will be able to predict these kind of scenarios, we will be able to predict that what would be the share prices look like in a coming day. So that's a very important tool which has to be used to, again, to minimize the risk involved in finance. So that is a very important thing. So if you look at the graph, you can see that every time the model is run, different results are produced. They are not same. It's not a straight line curve, or it's not something which is mathematically we can define and we can derive an equation for that. And if we can do that, that is a kind of deterministic model. When we involve probabilistic things into it, this uncertainty involved in that this kind of graph or phenomena, then we call it a stochastic model. Now the question is, why stochastic modeling in finance? Why we need stochastic modeling in finance? How it has become so important in the field of finance? There are two major criteria and two major reasons. The one is uncertainty of finance market. We know that a lot of uncertainty is involved in finance. One day something has happened in any corner of the world, the whole share prices will go down. Anything has happened to our own country, and our share market may go down and may go up, or it behaves very abruptly, and there is a lot of uncertainty involved in it. So people who are the main players, like investors, bankers, and many other people, these are the main players who want to predict the uncertainty, who want to know that what is going to happen tomorrow, right? So a lot of uncertainty tempted people to model these phenomena using the probabilistic or the stochastic models or the tools. And the second is the volatility of the finance market. Now the question is, what is volatility? To be very simple and straightforward, volatility means a lot of standard deviation, a lot of variability present, right? You can look at the present scenario of Adani shares, how they are going down. And if you look at the prices 2 months back, and if you look at the prices today, you can see that how much volatile is the share market and the finance market is. So due to the lot of volatility and due to the lot of uncertainty, and finance is something which is very important, core, that anybody would like to have more and more finances in their hand. So finance is a very important thing to be controlled. One, two, looking at the uncertainty and volatility in that market, we need to model it appropriately and efficiently. That can save us a lot of money, and that can give us a strategies to go ahead, and so that we can forecast that what can be our profits in coming times if we will invest this much amount in this kind of stock or option or anything else. So that's why stochastic modeling is very key feature or very key component of finance. Now the question is stochastic versus deterministic models. How they are different. So the prime difference between stochastic and deterministic representation is noticeable in the name stochastic itself. The word stochastic indicates a random probability distribution, whereas deterministic indicates the absence of randomness. When we don't consider the randomness, then that is kind of model as a deterministic model. So in randomness, we look into the consideration, we take into the consideration anything which is random, which we cannot say that it would happen tomorrow. So that is something random, which has probabilistic component very well assigned to it. But in deterministic models, we just predict a single outcome with some input of data. So that is the basic difference between stochastic and deterministic models. So stochastic versus deterministic, again the question. Now the question is how numerical methods are different than the regression models. If you look at the deterministic models and the stochastic models, the first thing which we can come into the mind is the numerical methods. You might have studied all numerical methods in which we approximate functions. We have X and Y values. We have a function, we have some values, and you try to predict that function with the help of the data which we have using the numerical methods. In that, we have not considered any probabilistic part into it. We have not considered any randomness into it. We just predict that model, or we approximate the form of the function using simple polynomials like second degree curve or third degree curve, depending on the nodes, depending on the data we have. So that is what the numerical methods. But when we look at the regression models, we have incorporated a random phenomena into it. And that's why we can see that how regression models are more popular than the numerical methods in economics, in finance, statistics, in insurance. So regression models have considered a functional relationship between two variables. One is the dependent variable, another one the independent variable. But a very important part has been incorporated there, that is the randomness of the error. We have incorporated one error component into the regression model, which makes it a stochastic model and which makes better than the numerical method. So that's why the regression models are more popular, more in use, even it is data science, even it is machine learning or any other models, they are more popular than the numerical methods. Why? Because one are stochastic models and one is deterministic models. So in one, we have just ignored the random phenomena, the random component, the noise part, which can come into the data, and we are not treating that part as a probabilistic part. So that is the major difference between stochastic and deterministic modeling. So now the question that where we can use stochastic models. We can start talking about disease modeling. If you heard about corona disease, when you look at any disease modeling methods, if you would not able to include the probabilistic part, the stochastic part, the model which you will give won't be the appropriate model or a good model, because every model has to be assessed at the end that how this model is working. So if we would be modeling anything without the stochastic components, that model cannot work as a good model. So it is disease modeling, stochastic part would come into the picture. It is finance, the stochastic part would come into the picture, because again, there is a randomness. We have witnessed the COVID waves, wave 1 and wave 2, how uncertain the whole world was. And if there is a lot of uncertainty involved, and we would ignore the stochastic component to create that model, we would be actually losing a lot of information which is there in that uncertain part. And that information is the important one to model the whole scenario. So it is disease modeling, it is finance, it is risk assessment, and insurance. So a lot of insurance, a lot of the stochastic part or the probabilistic part is assigned. So when we go to model the insurance phenomena like claim distributions or claim amounts or anything, we need to look into the data and we have to explore how probabilistically it is behaving, how we can able to model the randomness present into the data. And if it is agriculture, if it is economics, everywhere there's stochastic models we are using. The most popular and the models which works well than any other deterministic models which we have been using in the past days. Now the question is, what is financial modeling? So financial modeling is the process of estimating the financial performance of a project or business by taking into account all relevant factors, growth and risk assumptions, and interpreting their impact. It enables the user to acquire a concise knowledge of all the variables involved in financial forecasting. So that is what the financial modeling is. Now the question is, what is financial mathematics? Because financial modeling cannot be done without learning about financial mathematics. Now the question is, what is financial mathematics? So financial mathematics focuses on applying mathematical formulas and equations to financial problems, market modeling, and data analysis. With this strategy, financial professionals can better understand business performance, including profitability and growth potential. Financial mathematics is the application of mathematical methods to financial problems. Sometimes different names have been used, like quantitative finance, we call them quants, financial engineering, mathematical finance, and computational finance. These are the different names and the terminology which have been used for financial mathematics. It draws on tools from, so what are the major tools in financial mathematics? What do we need to study in financial mathematics? So it draws on tools from probability, statistics, stochastic processes, and economic theory. Additionally, investment banks, commercial banks, hedge funds, insurance companies, corporate treasuries, and regulatory agencies apply the methods of financial mathematics to such problems as derivative securities valuation, portfolio structuring, risk management, and scenario simulation. Quantitative analysis has brought efficiency and rigor to financial markets, and to the investment process, and is becoming increasingly important in regulatory concerns as well. So that's all about a very introductory PPT which I wanted to talk about. Now I'm open for any kind of questions if you have, because as I told you, I was not very much, anyways, I will stop sharing once. And now I'm open for any kind of questions from the student community or the teachers, or any kind of questions they would like to ask about the stochastic modeling. I'm open for questions now. Is there any questions? Ruchu ma'am, if you are speaking, you are muted there. I cannot hear you.
Wait a minute.
No questions. How many students are there who are interested in data analytics, who are interested to become a quant, who are interested to become, anybody, any questions?
Good afternoon, ma'am.
Good afternoon, Yukita ma'am.
Ma'am, my research area is stock prediction only.
Okay.
So my question is, how can I convert the other factors into data, other factors like news, effect of news on stocks and other events of.
Yeah, that is known as event. That is known as event analysis. That's a different branch. Every event is impacting the stock prices, right? So we
Yes,
need
right.
to look, yeah, and that whole thing has to be modeled. Like we have to look at the past data, and on looking at the past data, we have to use the stochastic models to create a model for that. So if there were many events were happening in the past, we can look at the past phenomena and we can create a stochastic model using Brownian motion or anything very important, which is most suited to that data. And that same thing can be implemented if there are similar kind of events happening in the, is there in the present day. So that's an event analysis, and all probabilistic models has to be implemented. So that's a different branch totally. But yes, we can discuss later on more on it. Yeah.
Okay, ma'am. Thanks. Thank you so much, ma'am.
Anybody else?
So, may I start?
Now,
Ma'am,
I would
everyone
like
wants
to
to
invite.
hear you live in JCRC.
Yes, ma'am. I would like to invite Dr. Sunil Srivastava sir for giving thanks to Dr. Jyoti Thanvi ma'am. Sir, please unmute yourself.
Thank you, Sumedha, and thank you, Jyoti ma'am. On the behalf of JCRC College, I, Dr. Sunil Kumar Srivastava, present here to express my vote of thanks to especially our eminent speaker, Professor Thanvi ma'am. Ma'am, thank you very much for accepting our invitation and presence here, and blessed us with your presence and knowledge. And indirectly, I want to say special thanks to you, ma'am. I am saying you after near about 7 years ago, I have seen you, and after 7 years, I am seeing you again on the screen live from Dubai. So
right now I'm in Jaipur. Right now I'm in Jaipur. I'm on leave. Yeah.
Okay.
Yeah.
Ma'am, one thing I also say, if time is money, then you have spent millions of us today, and your thoughts have truly inspired us. Thank you, ma'am, for this session and your knowledge and presence here. Thank you. Thank you, ma'am.
Dr. Srivastava, for giving me such a kind, thanks, because I don't feel that my talk was something which was very important and impacted students, but I am there. That's okay. It was a very short notice, and I think nothing much has been presented, but I'm thankful to you people for your invitation, and giving me such a warm welcome.
Okay, ma'am. Thank you.
Thank you.
For accepting our invitation in such a short time. Yes, or talk to our students. It is really a pleasure seeing you live.
Thank you.
Just
Ruchi ma'am, you are not properly audible. Lot of noises around, I think.
Everyone's phone and microphone and camera is on. Here.
Right. That is creating a lot of disturbance.
Ma'am, please accept this token of gratitude on behalf of JCRC Foundation.
Thank you, Sumedha. Thank you very much. I'm always a privilege to meet the JCRC friends. No, it is like my alma mater. I don't know why. Thank you.
Thank you so much, ma'am.
Thank you, everyone. Thank you.
Thank you so
soon.
much, ma'am.
Thank you. Thank you.
Now I want to thank Sumedha and Manasvi who coordinated the event so well. Ma'am, these are our first year students, Sumedha, Sharma and Manasvi. They coordinated the whole well.
Very good. Yeah.
Thank you, ma'am.
Thank
They
you,
also
ma'am. Thank you
deserve
so
a
much.
Yeah, God bless you both. God bless you.
Definitely, ma'am.
Keep growing.
Thank you, Sumedha. Thank you, Manasvi.
Thank you, everyone. Can I leave now?
Yes, ma'am. You can leave.
Thank you, Ruchi ma'am. Bye. Bye.
Thank you so much, Sumedha.
Yes, ma'am.
Thank you,
Thank you,
Manasvi.
Sumedha and Manasvi.
And good job,
Thank
guys.
you, ma'am. Thank
Seriously,
you.
very good job.
Thank you, ma'am.
Okay.